Welcome to day 1 of the STL Mastery course. Today marks the beginning of our deep dive into one of the most powerful features of modern C++, the standard template library. Our session is titled Introduction to STL, What, Why, and How. We will explore what STL actually is, why it's a game changer for C++ developers, and how we can start using it today. By the end of this module, we will be writing our first STL based program and we will have our development environment fully set up for C++ 17 or C++ 20. Let's begin with the objectives of today's session. First, we will understand what STL is and why it is a fundamental part of C++ programming. Then we will explore its key components. This will include containers, iterators, algorithms, and more. Next, we will go over setting up our development environment for STL support. Whether you are using an IDE like code : blocks or a lightweight editor like VS Code. Finally, we will apply what we have learned by writing a simple program using STL containers and algorithms. So what exactly is the STL? STL stands for the Standard Template Library, and as the name suggests, it's a template-based library that's part of the standard C++ library. STL provides a rich set of classes and functions that make handling data structures and algorithms easy, efficient, and consistent. Rather than reinventing the wheel every time, STL lets us use well-tested and optimized implementations of containers like vectors and maps and algorithms like sort or find. It's generic, which means it works with any data type thanks to templates. Now that we know what STL is, let's talk about why it's so useful. First of all, productivity. STL lets us write less code without sacrificing performance. Need a sorting algorithm, it's already built in. Want a dynamic array, just use vector. Second, STL is highly optimized. Most STL code is as fast or sometimes even faster than code you would write manually. It's also reusable and reliable thanks to years of testing and standardization across compilers. And finally, STL is a standard, meaning every modern C++ compiler supports it. That makes our code portable, consistent, and easy to share. STL is composed of 5 main components. First, containers like vector, map, set, PQ, and others. These are used to store data in different structures. Second is the iterators, which are like pointers that help us navigate through containers. Third is the algorithms. These include things like sort, find, count, and accumulate. They work seamlessly with containers and iterators. And fourth is function objects or functors, which allows us to create custom behavior when working with algorithms. And finally, STL includes several utility tools like pair, tuple, bitset, and newer additions like optional variant and any in C++ 17. Let's take a look at how STL is used in the real world. In competitive programming, STL is indispensable. Fast implementations of set, map, and heaps make solving problems efficient. In system design, STL helps with implementing caches, indexing systems, task queues, and more, all with minimal code. And in real-world software development, STL is everywhere, from text editors to financial software, anywhere where structured data is being handled. Let's now set up our development environment. If you are using a C++ IDE like docs or dev C++, go into the settings and look for compiler flags or compiler options. You will want to enable support for the modern C++ standard, either C++ 17 or C++ 20, by adding the flag std equals to C++ 17 or std equals to C++ 20. This will allow you to use all modern STL features we will cover in this course. Prefer VS Code? No problem. Make sure you install the C++ and Code Runner extensions from the Extensions Marketplace. To compile your program, use the integrated terminal. You will run the command g++ std assign std equals to C++17 main.cpp -o main followed by dot and / main to execute it. VS Code is lightweight and fast, and with the right setup, it's perfect for STL development. Don't want to install anything? That's perfectly fine. There are several powerful online compilers you can use. Godbolt.org is fantastic if you want to see how your C++ code compiles into assembly. Great for learning. Online GDB gives us a full debugger inside the browser, and Replit is excellent for collaborative coding and running programs online. Any of these platforms will work just fine for today's hands-on. Here's a basic STL program in C++. We start by including the necessary headers, vector for our container, and algorithm for sorting. We declare a vector of integers, initialize it with some values, and then sort the vector in ascending order. Finally, we print the sorted list using a range-based for loop. This is STL at its simplest, containers and algorithms working together. Let's walk through what this code is doing. Hash include vector brings in a vector container class. Sort nums.begin, nums.end sorts the vector using iterators, a key STL concept. We use a vector int to store our data and a range-based for loop to print each element. This is both readable and efficient. You will use this style often throughout the course. Now it's your turn. Write a short program where the user inputs 5 integers. Store those integers in a vector, then sort the vector and print the numbers, but in reverse order. To do this, use sort followed by the reverse function. This small exercise helps you get comfortable with STL syntax and with compiling and running C++ code in your setup. Before we wrap up, here are some quick tips. Always prefer STL containers over raw arrays. They are safer and come with useful methods. Only include the headers you actually need. This keeps compile times low and code clean. And use the while flag when compiling. It enables all compiler warnings, helping you catch bugs early in the development process. To go deeper into STL, here are some excellent resources. cppreference.com is your go-to reference for everything in the C++ standard library. hackingcpp.com offers visual guides and cheat sheets that are great for quick revision. And godbolt.org, a compiler explorer, helps you understand how your C++ code translates under the hood. It's a powerful tool for understanding, optimizing, and performance. To summarize today's session, we introduced the STL and its importance in modern C++ development. We learned about the 5 core components of STL and how they work together. We covered multiple ways to set up your development environment and wrote our first STL-based program. Tomorrow we will build on this foundation by diving into templates and iterators, 2 crucial building blocks for mastering STL. Welcome to day 2 of our 42-day STL Mastery course. Today we are going to unlock 2 of the most foundational concepts that power the entire standard template library, templates and iterators. These tools help us write generic, reusable and efficient code that does not just work for one type or situation but can be applied across a wide range of scenarios. If you have ever used a vector, map or stack in C++, you have already benefited from templates and iterators, even if you didn't realize it. So let's explore how they actually work under the hood and how you can yield them with confidence in your own code. Let's take a moment to look at today's learning objectives. First, we will gain a solid understanding of what templates are and why they matter in C++. We will compare function templates to class templates and see where each is used. Next, we will discover how STL is fundamentally built on the idea of templates. Without them, generic containers like vector int or map string int would not exist. Then we will dive into iterators, powerful tools that allow us to navigate through STL containers efficiently. Finally, we will go beyond basic syntax and examine different types of iterators: input, output, forward, bidirectional, and random access. Understanding these categories will make us a more flexible and efficient programmer. So why do we even need templates? Imagine you wanted to write a function that adds two numbers. You could write one for integers, one for floats, another for doubles, but that's not scalable. Templates solve this by enabling generic programming. They allow us to write one version of a function or class that works with any data type, and the compiler generates the type-specific code behind the scenes. This not only reduces code duplication but also improves readability and maintainability. In STL, this is crucial. When you use vector int or vector string, you are actually using the same underlying class template, just instantiated with different data types. Templates are the reason STL containers are so flexible and powerful. Let's start with function templates. Here's a simple template function called add. It accepts two parameters of type t, a placeholder for any data type. When we call this function, the compiler automatically deduces the type based on your input. If you pass integers, it becomes an int function. If you pass floats, it becomes a float function. The result: one function definition, unlimited use cases. This improves consistency, reduces bugs, and is especially useful in competitive programming or system design, where efficiency and clarity are key. Now let's talk about class templates. Class templates follow a similar idea but on a larger scale. They define a blueprint for an entire class that can work with any data type. In this example, we have defined a box class that can store any type t. We can use this class to create a box int, a box double, or even a box string. Class templates are widely used in STL containers. For instance, vector, map, and stack are all class templates. This allows them to store anything, from primitive types to user-defined objects, while maintaining type safety and performance. The entire STL is essentially a massive demonstration of the power of templates. Let's look at a few examples. Vector t stores sequence of any type. Map k, v holds key value pairs of any type combination, and pair t1 t2 bundles two values together. Thanks to templates, STL gives us a set of incredibly versatile tools that work with virtually any data structure or algorithm. We don't need to write separate versions for integers, floats, or strings. We write it once and let the compiler handle the rest. That's not just powerful, it's elegant. Now let's shift our focus to iterators. If containers are like collections of data, then iterators are the navigators that help us move through them. We can think of iterators like smart pointers. They allow us to access elements, move forward or backward, and even manipulate data, all while abstracting away the underlying structure of the container. For example, a vector and a list store data differently, but we can use them the same iterator syntax to loop through them. This uniformity is one of STL's greatest strengths. Iterators aren't one size fits all. In fact, there are 5 main types, each suited for different containers and operations. First, we have input iterators like iStream iterator, which read data one element at a time. Then output iterators like OStream outer iterator, which allow us to write data sequentially. Forward iterators can move in one direction and are used in structures like forward list. Bidirectional iterators, as the name suggests, can go both forward and backward. These are used with list, map, and set. Finally, we have random access iterators, the most powerful type. These support pointer-like operations like indexing and arithmetic. Containers like vector, deque, and array use them. Understanding these types helps us choose the right container and write more optimized code. Here are two common ways to iterate over a vector. The first is the traditional method using an iterator object. We declare an iterator, set it to the beginning of the vector, and loop until the end. The second method uses a range-based for loop with the auto keyword. This is cleaner, more modern, and often preferred when we don't need to modify the elements. Both are valid, and choosing one over the other depends on the context. If you are writing older code or working in environments without full C++11 support, you might stick with the classic method. Otherwise, embrace the newer syntax for cleaner and more readable code. Now it's time to apply what we have learned. Try writing a swap function using templates. This will help reinforce the concept of function templates. Next, create a templated class called container T that can store and return any type of value. Practice iterating through a vector and a list using both standard and reverse iterators. And here's a challenge. Reverse a vector without using STL's rbegin or std::reverse. This will test your understanding of both iterators and indexing. Let's summarize what we have covered today. Templates are the backbone of STL. They allow us to write flexible, type-safe, and reusable code. Function and class templates simplify our code base and make it easier to maintain. Iterators provide a unified way to access elements in STL containers, regardless of their internal structure. And lastly, knowing the different types of iterators helps us optimize our code and choose the right approach for every problem. Want to go a little deeper? Explore iterator traits, which are used to determine iterator category and properties at compile time. Try creating your own custom iterator class for a data structure. It's a great way to understand how STL does it behind the scene. Also learn about iterator invalidation, which occurs when changes to a container make existing iterators invalid or unsafe to use. This is especially important in competitive coding and interviews. To reinforce today's concepts, here's your assignment. Write a function template max of 3 to find the largest of 3 values. Build a class point t with a member function to calculate distance between 2 points. This is a great way to use class templates practically. Traverse both a deque and a list using iterators forward and reverse. And finally, take on the bonus challenge. Reverse a vector without using built-in STL methods like rbegin or reverse. This assignment will not only test your understanding but also prepare you for more complex topics ahead. Welcome to day 3 of our STL course. Today we will dive into one of the most widely used and powerful containers in C++, the vector. By the end of this session, you will not only understand how vectors work under the hood, but also you will be able to write clear, efficient code using them. Vectors are dynamic, versatile, and form the backbone of many real-world applications. Let's get started. Here's what we will cover today. First, we will understand what a vector really is, how it compares to arrays, and what makes it so powerful. Then we will explore how to declare and initialize vectors in various ways. We will follow that with vector insertion techniques, element access methods, and key behavioral insights about how vectors grow. Finally, we will solidify our understanding through a coding task and some practical challenges. Let's start with basics. A std::: vector is part of the standard template library and acts like a dynamic array. Unlike static arrays, vectors can grow or shrink in size dynamically. They store elements contiguously in memory, making them cache-friendly and fast for traversal. With built-in support for resizing, inserting, and accessing elements, vectors eliminate the pain of manual memory handling. This is why they are often a go-to choice for developers in both beginner and advanced projects. Vectors can be declared in multiple ways depending on what we need. We can start with an empty vector using vector int v. We can prefill a vector with default values using vector int v5 to create a vector of size 5 filled with 0. We can also provide an initial value like vector int v5,10, which gives us a vector of 5 tens, and with initializers list we can create and initialize in one go using curly braces. This flexibility is a huge advantage when working with different types of data or starting conditions. Inserting elements into a vector is done primarily using pushback, which appends elements at the end. It's very efficient, amortized constant time. For more control, insert lets us place elements at specific positions, though it's costlier as it might shift existing elements. Behind the scenes, when the vector runs out of allocated space, it doubles its capacity, reallocating memory and copying all elements to the new space. That's why frequent mid-vector insertions can be expensive. So always choose the right insertion method based on your use case. Accessing elements in a vector is intuitive. We can use the square bracket notation like vi for fast access, but it does not perform bounds checking. If we go out of range, it can crash our program. For safer access, we use v.addI, which throws an exception if the index is out of bounds. We also have v.front and v.back to quickly get the first and last elements. For robust and production-ready code, we prefer using at unless performance is absolutely critical. This is a common area of confusion: size versus capacity. The size of a vector is how many elements it currently holds. The capacity is how much memory it has allocated, often more than the size, to allow for future insertions. When we keep adding elements and a vector exceeds its capacity, it allocates new memory using double and copies everything over. Understanding this is essential for writing efficient code. We can manage it using functions like reverse to pre-allocate space or shrink to fit to reduce memory usage. Let's walk through a simple program. We include vector to use the container and algorithm for sorting. We declare a vector with 3 elements, then use pushback to add another. Next, we sort the vector and print the elements using a range-based for loop. This snippet shows the real power of vectors: easy resizing, built-in algorithms, and clean syntax. If you are new to STL, this is your first taste of how expressive and concise C++ can be. Time for a mini challenge. Create a vector of even numbers from 2 to 20. Then insert a new value, say 99, at the second position using insert. Finally, print the entire vector using add instead of square brackets. This quick challenge will help you get comfortable with basic operations and ensure you understand the differences between access methods. Now it's your turn to build something a bit more substantial. Write a program that reads n numbers from the user into a vector. Once all values are collected, sort the vector in ascending order using sort. Then print the elements in reverse order. Bonus points if you handle edge cases like empty input or duplicate values. This task is designed to help you reinforce what you have learned so far: input, manipulation, and output using vectors. Let's take a step back and reflect. When would you choose a vector over a regular array? How do vectors compare in terms of safety and performance? What are the trade-offs when using insertions at various points? And Finally, think of real-world applications. Vectors are perfect for undo history in editors, users' input tracking, and maintaining logs. Their versatility makes them invaluable. Here's your homework. Write a function to reverse a vector in place. No new vector allowed. Next, remove all even numbers from a vector using erase remove idiom. And for a bit of a stretch, try defining a vector of structs representing students with names and marks. Sort them by marks and print the top scorer. This blends vector concepts with custom data structures, just like you will do in real projects. To wrap up, vectors are a must known in STL. They are dynamic, safe, and offer powerful functionality out of the box. Today we covered declaration, insertion, and access, all of which form the foundation for more advanced operations. In the next session, we will explore how to modify and manage vector more like a pro. Till then, keep practicing and experimenting. Happy coding! Hey there, and welcome back to our STL mastery journey. Today is day 4, and we are diving into a really important and practical part of the C++ standard template library: vector modifiers and capacity. We will often find ourselves using vectors for dynamic data, and knowing how to modify them efficiently can make our code cleaner, faster, and much easier to maintain. We will also uncover how vectors handle memory allocation behind the scenes, an essential piece for writing high performance applications. Let's take a look at what we are aiming to learn today. We will start with vector modifier functions like insert, erase, and emplace back, which allow us to manipulate the contents of our vector in powerful ways. Next, we will talk about memory management, including how vectors grow, what capacity means, and how to reverse or shrink memory proactively. Finally, we will explore best practices and common pitfalls, especially around iterator invalidation. And of course, we will end with real-world code examples and hands-on activities to reinforce our understanding. C++ vectors can come equipped with a rich set of modifier functions. These aren't just bells and whistles, they are essential tools you will use daily. Functions like pushback and popback add or remove elements from the end of the vector. Dot insert lets us place element at any position, while erase helps us remove specific entries. Then there's clear for whipping the entire container and resize for adjusting the number of elements. And finally, the modern C++ starts emplace and emplace back, which create objects directly in place, avoiding unnecessary copying or moving. Each of these has specific use cases, performance implications, and behaviors that will break down today. Let's walk through a concrete example to see these modifiers in action. We start with a simple vector of integers 1, 2, 3. We use pushback 4 to add an element to the end, making it 1, 2, 3, 4. Then popback removes the last element. We are back to 1, 2, 3. Next, insert v.begin, 0 places a 0 at the beginning, while erase v.begin plus 1 removes the second element. Finally, clear whips the entire vector. Notice how intuitive this sequence is. Each line changes the vector in a clear and controlled way, but underneath there are performance and memory considerations we will soon explore. Now let's talk about a more efficient alternative to pushback, emplace back. Imagine you are using a custom type like a point start with x and y values. When you use pushback point 1, 2, a temporary object is created, then moved or copied into the vector. But with emplace back 1, 2, the object is constructed directly in the memory of the vector. No temporary object, no extra copy. This subtle difference becomes a big win in performance critical code, especially in loops or large datasets. Always prefer emplace back when dealing with user-defined types. Let's shift gears to something less visible but equally important: vector capacity. The size of a vector tells us how many elements it currently holds, but capacity tells us how much memory it has reserved. This matters because vectors grow dynamically, and when they run out of space, they allocate new memory and copy all the elements over, which is expensive. Using reverse AND lets us pre-allocate memory, avoiding those costly reallocations. Shrink to fit does the opposite. It tries to reduce unused memory after shrinking the size. Understanding and managing capacity helps us write smoother, faster programs, especially in data-heavy context. This slide shows a common behavior: exponential growth in capacity. When we push elements into a vector in a loop, it does not grow one by one. Instead, it often doubles its capacity to avoid frequent reallocations. In this example, every time we call pushback, we print the size and capacity. You will notice that the capacity jumps even if size increases linearly. This is a deliberate design choice for performance, but it also means you might allocate more memory than needed, hence the value of rewards and shrink to fit. Here's a common point of confusion: resize versus rewards. Let's clarify. Rewards 100 allocates memory for 100 elements, but does not add them. The size stays the same, 0 if it was empty. On the other hand, resize 100 actually inserts 100 default initialized elements into the array or the vector. If you are prepping a vector for incoming data, use rewards. But if you need the elements in place, maybe for initialization or fixed length buffers, go for resize. Now it's time to put your knowledge to the test. Write a function that does three things. First, insert -1 before every odd number. Then remove all even numbers from the vector. Finally, resize the vector to only 5 elements. This exercise will help reinforce your understanding of how insert, erase, and resize interact, and how every operation affects both size and capacity. Here's another challenge: test the performance of emplaceback against pushback using a custom class like person. Use the chrono library to measure time taken during insertion. This will give us first-hand experience of how emplace really shines when dealing with constructors and object creation. It's one thing to know it in theory. Now you will see the numbers yourself. Let's recap what we have learned. You can now use vector modifiers like insert, erase, and emplaceback confidently. You understand how vector capacity works and how to optimize it with reverse and resize. You know when to use emplace over push and how to manage vector growth for performance. And perhaps most importantly, you are now aware of the subtle costs and pitfalls of careless vector manipulation. To reinforce today's lesson, here are a few practical exercises. First, build a basic book catalog system that uses pushback, insert, and erase to manage books. Second, simulate an undo feature using popback. And finally, for deeper learning, simulate a dynamic array using raw pointers and compare the complexity with STL vectors. This will help you appreciate why STL exists and how much heavy lifting it does behind the scenes. And that's a wrap for our day 4. Today we moved beyond just using vectors and learned how to control them like pros, modifying their content, managing memory, and optimizing behavior. Remember, mastery of modifiers and capacity management makes our code not only more elegant but far more efficient. Feel free to ask questions, share your thoughts, or jump straight into the activities. I will see you in the next session. Hello and welcome to day 5 of our 42-day journey to the Standard Template Library or STL. So far we have explored vectors in depth, covering their declaration, capacity management, and modifiers. Today we take it a step further. We will focus on how we iterate through vectors efficiently, safely, and idiomatically in modern C++. Here's what we will aim to achieve today. First, we want to understand all the common methods used to iterate through a vector, from the traditional index-based loop to the more modern and safer range-based loop. Next, we will compare each approach, pointing out where it shines and where it might introduce bugs or inefficiencies. We will also dive into common pitfalls, those subtle mistakes that can lead to hard to find bugs such as iterator invalidation or accidental copies. Finally, we will wrap up with best practices that we can apply immediately in our own C++ projects to improve performance and readability. Before we move forward, let's take a quick refresher. Over the last few days, we have built a strong foundation in vectors. We have learned how to declare vectors, how to insert and access elements, and how to use modifiers like pushback, insert, and erase. We also touched on memory management with functions like reverse and shrink to fit. Now, as a quick exercise, can you recall three vector modifiers and describe what they do? Take a moment and think. This will help reinforce your understanding before we start iterating. C++ gives us a variety of ways to loop through vectors, each with its use cases. We will begin with the index-based loop, the most classic form. Then we will move to the range-based for loop introduced in C++11, which reduces boilerplate and is less error-prone. Next, we will explore iterator-based loops, essential when working with STL algorithms or when you need direct access to memory addresses. We will also look at const iterators, which enforce read-only access, a great tool for safe coding. Finally, we will examine reverse iterators, which allow traversal from the end of a vector to the beginning. Let's start with the most fundamental method, the index-based for loop. This is where we manually access each element using vec_i, running from index 0 to vec.size -1. It's highly flexible, letting us skip, reverse, or modify elements conditionally. But it also comes with a risk. A typo in your loop condition or using an invalid index can lead to undefined behavior and crashes. Always ensure your loop limits are correct and prefer using vec.size instead of hard coding limits. Introduced in C++, the C++11, the range-based for loop simplifies syntax and improves readability. You simply write for int val :vec and C++ will handle the iteration behind the scenes. However, this gives us a copy of each element, meaning changes inside the loop won't affect the original vector. To modify elements, use for int val :vec. This loop is ideal when you are reading or modifying all elements uniformly without worrying about indices. The iterator-based loop is another core technique. Here we use vec.begin and vec.end to define the start and end of the range. This method is especially useful when combining loops with STL algorithms like erase, find, or insert. Though more verbose than the previous methods, it offers precise control and compatibility with the full power of STL. Be cautious with syntax and dereferencing. Small mistakes can cause major issues. Sometimes we want to iterate without modifying the vector. That's where const iterators come in. They enforce read-only access to the container during iteration, preventing accidental changes. This improves code safety and helps other developers understand that the data is not being altered. Use cbegin and cend instead of begin and end for this. It's a good habit to use const iterators in functions that only read data. Now let's flip things around. Reverse iterators allow us to iterate from the end of the vector to the beginning using rbegin and rend. They are extremely handy for problems like finding the last occurrences of an element or when processing data in reverse order. Just remember R begin points to the last element and Rn points to point one before the first. Like regular iterators, reverse iterators also work well with STL algorithms. Now that we know how to iterate, let's look at what not to do. First, modifying a vector while iterating through it can invalidate iterators. If you erase an element while inside a loop, you must update the iterator. Second, accessing a vector using unchecked indices can cause out-of-bounds errors. Use @I if safety is a concern. Third, inserting or erasing during insertion changes the internal structure of the vector, often causing bugs if you are not careful. Always test iteration logic thoroughly and refer to STL documentation when in doubt. Here are a few golden rules. Prefer range-based loops when possible. They are safe, short, and expressive. Use auto ampersand and const auto ampersand to avoid unnecessary copying and to ensure clarity in intent. Avoid modifying a container mid-iteration unless you absolutely know how to do it safely. And finally, master the erase remove idiom. It's a common STL pattern to remove items from containers efficiently. Let's reinforce today's learning with some hands-on practice. Try printing a vector using all 5 iteration methods we discussed. Then reverse print only even numbers. This will test your understanding of both filtering and reverse iterators. Next, write a loop to safely remove negative numbers. Lastly, debug a deliberately broken loop to understand common iteration errors in real-world scenarios. Let's take a step back. Why is iterator safety important? It's not just about preventing crashes, it's about building robust, maintainable code. Think about which iteration style you naturally gravitate toward and why. Tomorrow we will go deeper with real vector-based coding problems. So keep these patterns in mind, they will come in handy. Your homework for today is simple but valuable. First, implement a function called remove duplicates, which efficiently clears duplicate values from a vector. Next, solve at least 3 lead code problems that require iteration through vectors. Finally, spend some time on cppreference.com, especially the section on iterator invalidation. It's a gold mine of STL wisdom. And that wraps up day 5. Great work on mastering vector iteration. You now have a complete toolkit to traverse, filter, and manipulate vectors with confidence. As always, if you have questions, drop them in the discussion or bring them to the next session. Keep practicing, and I will see you in day 6 for a full set of vector-focused coding challenges. Hello and welcome to day 6 of our 42-day STL Mastery course. Today is where we shift gears a little. We are moving from theory to full-on practice. Vectors are one of the most versatile and commonly used STL containers, and today we will not only solidify your understanding of them but also apply our knowledge in real-world scenarios, from basic manipulations to more thoughtful problem solving. This is our vector test drive today. Let's dive in. Let's begin with our objectives for today. First, we will reinforce our foundational understanding of vectors, making sure you are comfortable with how they are declared, modified, and accessed. Second, we will move into active problem solving where you will implement what you have learned in code. Third, we will highlight common mistakes and pitfalls so we know what to avoid in interviews and real world applications. And finally, the goal is to boost our confidence when using vectors so that they become second nature in our STL toolkit. Before we dive into problems, let's refresh a few critical concepts. We should already be comfortable with how to declare and initialize a vector, either with default values, specific size, or initializer list. Access methods like the subscript operator, the add method for bounds checking, and accessors like front and back are essential. You also need to know modifiers like pushback to insert at the end, popback to remove the last element, and insert, erase, and clear for more control. Don't forget the difference between size, the number of actual elements, and capacity, which refers to the amount of memory currently allocated. Understanding these will help you not only write functional code but efficient code too. We will start with some warm-up problems to activate our STL neurons. These are relatively simple tasks but incredibly useful to build fluency. Try writing a function to sum all the elements in a vector. It's straightforward but a great place to start testing loops and iterators. Next, reverse a vector using both a manual loop and STL's reverse algorithm. Compare them. Try inserting an element at a specific position. Remember that indexing matters. Implement duplicate removal in sorted vectors. Use STL tricks like init combined with erase. And finally, the max and min values in a vector, both manually and with STL functions. These tasks may be simple, but they are core building blocks for everything ahead. Are you ready to level up? Let's move to intermediate challenges. First, try rotating a vector to the left by k places. Do it manually without building rotation functions at first. Then merge two sorted vectors into one sorted, of course. Don't forget to handle edge cases like unequal sizes or empty inputs. Next, compute a running sum where each element becomes the sum of itself and all previous elements. This is a great test of accumulation and loop control. The second largest element problem is a common interview favorite. Can you find it in one pass? Finally, try creating a frequency counter, either using a vector or combined with a map. This is an intro to combining STL containers for real utility. Vectors are simple until they are not. Let's address a few common mistakes that trip up even experienced developers. First, be careful with index out of bound errors. The subscript operator does not throw exception. At does. A lot of people confuse size and capacity. Size is how many elements are actually there. Capacity is how much memory has been reserved. If you are using vectors, don't forget to clear or resize them, or you might be building on top of slate data. And a big one, iterator invalidation. If you use insert or erase, it may invalidate iterators you are using in loops. This leads to subtle and painful bugs. Be mindful of this. Avoiding them will make your STL usage clean and professional. Now it's time to switch gears and get hands-on. You will be solving a series of problems. We recommend picking at least 4 to 6 from platforms like LeetCode, HackerRank, or Gigs. You can also use the Code Sandbox or your local IDE. Focus on writing clean code, testing with edge cases, and following the problem constraints. This is where you apply everything from the past 5 days and build real confidence. If you hit errors, don't worry. Bugs are your teachers today. For those who finish early or want a challenge, here's your stretch problem. Implement a sliding window maximum algorithm. You will be given a vector and a window size k, and your task is to find the maximum element in every sliding window of size k. Now the catch is, do this without using the DQ container or other advanced tools. Brute force it using just vectors. It may not be optimal, but it will push your logic and STL command. Try to make it efficient, and we will look at how to optimize it in upcoming sessions. Once you have worked through the lab and stretch problem, we will come together as a group to debrief. We will review the most interesting and tricky questions, discuss how people approach them and analyze different solutions. This is a great time to learn from your peers. Often, someone's shortcut or insight will help you improve your own coding process. Feel free to ask questions or share alternate solutions. This is a safe place for growth. Before we wrap up, here's your homework. Solve at least two intermediate level problems related to vectors. Pick something that challenges you. Explore the difference between using vector int and using and vector int. Understand memory layout, access patterns, and use cases. And optionally try implementing a matrix transpose using a 2D vector. It's a fantastic way to deepen your knowledge of nested vectors and grid manipulation. And that brings us to the end of day 6. You have done some solid work today, reinforcing core concepts and applying them through hands-on problem solving. You have, if you have any questions or if there were problems you struggled with, now's the time to ask. Don't hesitate to revisit today's lab later or discuss solutions with peers. Thank you for your focus and participation, and great job taking your STL skills to next level. Hello and welcome to day 7 of our standard template library course. Today marks an exciting milestone. We are diving into our first mini project. The goal is to build a student database using the std::vector container. By doing this, we will consolidate everything we have learned so far during week 1. You will get a chance to design, implement, and debug a small functional program that mirrors a real-world use case. This project is all about applying your skills, working with structs, vectors, input-output operations, and iterators, all in one cohesive system. Let's get started. This project isn't just about coding, it's a structured review of essential STL concepts. First, we will revisit vector operations like pushback, indexing, and iteration. You will also learn how to define and use structs to represent student data. Iterators and range-based loops will come into play when displaying or modifying data. Input and output handling will be key for interactivity. We will also explore sorting using custom comparators, which introduces more advanced vector manipulation. And finally, you will practice organizing your code into modular functions, a crucial step for writing clean, maintainable code. To manage student data, we start by creating a simple struct. This student struct contains 3 fields: an integer for roll number, a string for the student's name, and a float for marks. Structs allow us to treat related data as a single unit. Once defined, we can create a vector of student objects to store our database. This approach makes our code more scalable and easy to understand, as each element in a vector represents one student with all their associated information. Here's what we will be building. First, we need a way to add new student entries to our database. Then we should be able to display all the students stored in a vector. Next, we will implement a search function to locate a student by their roll number. Once found, we should be able to update their data, such as name or marks. We will also create a delete option to remove a student record from the list. For an extra challenge, you can add functionality to sort students, perhaps by marks in descending order. And finally, we will give users the ability to exit the problem gracefully. To make the program user-friendly, we will build a menu interface. Think of it like a command line dashboard. Inside a while true loop, we display the menu options repeatedly until the user chooses to exit. This interface prompts the user to enter a number corresponding to their desired action: add, view, search, and so on. Then, based on their input, the program will call the relevant function. This modular menu system not only helps users navigate the program, but also keeps your code clean and well structured. Let's break down the first two features, adding and displaying students. For adding, prompt the user to enter roll number, name, and marks. Store this data in a student struct and then push it into the vector. Displaying students is straightforward. You loop through the vector using a range-based or traditional iterator loop, printing each student's data neatly. These two operations form the backbone of your database and are the perfect place to begin your implementation. Searching is our first use case that involves decision-making logic. You will iterate through the vector looking for a student whose roll number matches the input. The ideal way to do this is with std::find if and a lambda function. Once a student is found, we can prompt the user to input new details, maybe a new name or updated marks, and assign them to the appropriate fields. This teaches us how to manipulate existing vector elements and reinforces concepts like conditional logic and lambda usage. Deleting records follows a similar pattern to searching. Use std::findIf to locate the student, then remove them using the erase function. Make sure to handle edge cases like if the student isn't found. Sorting adds a function, slightly more advanced twist. With std::sort and a custom comparator lambda, you can sort students based on marks or names. It's a powerful example of how STL and custom logic work together for real-life use cases. Here's a sample of how your program will look when executed. The menu options are clearly displayed and the user can select what they want to choose. For example, entering 1 allows them to add a new student by entering a roll number, name, and marks. A success message confirms the operation. Keeping your interface clean, informative, and friendly goes a long way in improving the user experience. Now that your program works, it's time to test it thoroughly. Try adding multiple students, then viewing the list to ensure data is stored correctly. Test what happens when you try to search or update a non-existent roll number. Delete a student and check whether they were removed successfully. Finally, sort your list and confirm the order is correct. These test cases help us identify bugs and edge cases, ensuring our code is reliable. Here are some practical tips. Use getLine for name input to handle full names with spaces. Don't shy away from using auto and range-based loops to simplify your code. Always break your code into small, single-purpose functions. It makes debugging easier. And make sure to validate all user inputs before using them, especially in the menu. This attention to detail will help you write cleaner, more resilient code. Are you feeling ambitious? Add some more stretch goals. For instance, save and load your student data from a file using file IO. You could also replace the vector with a std::map for faster lookups by roll number. Implement grading logic based on marks to assign letter grades or GPA, or introduce auto-incremented roll numbers to streamline student entry. These extra features push your C++ skills further and simulate real-world application development. By the end of today, your goal is to have a complete functioning student database using vectors. This project is a strong foundation. It demonstrates your ability to apply STL concepts to real-world coding tasks. You will leave this session having practiced struct design, vector operations, user interaction, and algorithmic thinking. Debug it, polish it, and be proud you have just built your first mini STL project from scratch. Welcome back to our 42-day journey into mastering the standard template library in C++. We have already explored vectors in depth, and now we are going to meet their flexible cousin, the DQ. Today is day 8, and our focus is on understanding what a DQ is, how it functions under the hood, why and when we would choose it over vectors or lists, and of course, how to use it effectively in real code. By the end of this session, you will not only understand a DQ, but also be ready to solve real problems with me. A DQ or the double-ended queue is a highly versatile container that allows us to insert and delete elements efficiently at both the front and back. It's a sequence container, just like a vector or a list, but with some key differences. Think of it as a hybrid. It gives us fast insertions at both ends like a list and random access like a vector. So if we ever need the benefits of both, the DQ is a perfect choice. We will explore exactly how and why next. Now let's peek under the hood. Unlike vectors, which rely on a contiguous block of memory, DQs use a segmented memory model. That means they allocate multiple smaller blocks dynamically rather than trying to grow one large contiguous chunk. This difference allows us to insert elements at the front without shifting the entire container, unlike with vectors. This structure makes DQs especially useful in scenarios where we constantly modify both ends of the sequence. Working with a DQ in C++ is straightforward. The interface is quite similar to that of a vector, with a few key additions. We can insert at the back using pushback and at the front using pushfront. Likewise, we can remove elements using popback or popfront. For accessing elements, we have front, back, at index, and the subscript operator. The queues also support clear, empty, and size, which make managing them quite convenient. Here's a basic example to show how we can use a DQ. First, we push a 10 to the back and a 20 to the front. So now our DQ contains 20 followed by 10. When we print the front and back, we get 20 and 10. Then we remove the front and back and we are left with an empty DQ. This illustrates how cleanly and symmetrically a DQ works from both ends. Now let's look at some practical use cases. One of the most common is solving sliding window path problems, where we need to insert and remove elements from both ends of a sequence. DQs also help in implementing undo and redo systems where actions are pushed and popped depending on user behavior. They are also great in palindrome checking, where we compare elements from both ends, and even in task scheduling, where we can dynamically add or remove tasks based on priority. In short, DQs show up in many real-world applications. So when should we use a DQ? The general rule is, if we need fast insertions and deletions at both ends, and we also want random access to elements, then the DQ is the ideal container. If our problem involves a lot of insertions or deletions in the middle, a list might be better suited. DQs really shine when we work with problems where the ends are active but the middle stays mostly untouched. This table gives us a clear comparison of vectors, lists, and DQ. Vectors provide fast random access and are efficient for back insertions, but struggle with insertions at the front. Lists excel at front, back, and even middle insertions, but don't support random access. DQs sit right in the middle. They offer random access and are efficient at both ends, but not optimal for middle insertions. Also, unlike vectors, DQs don't store elements in contiguous memory blocks. Let's try a hands-on exercise. We will insert integers into a DQ using both push front and push back. After every insertion, we will print the front and back elements, and for a bonus challenge, let's remove all numbers greater than 100 from both ends of the DQ using a loop. This exercise helps reinforce our understanding of insertion, access, and conditional removal. To sum it up, DQs are highly flexible containers, giving us the best of both vectors and lists. They are efficient for front and back operations and allow us to access elements by index. They are ideal for real-world problems like undo systems, task scheduling, and sliding window algorithms. For homework, let's explore using DQ with iterators and try out STL algorithms like reverse, remove if, or rotate. Also take a moment to explore the official C++ documentation to deepen your understanding. Up next, we will explore the list container and how it differs in structure and usage. See you in day 9. Welcome to day 9 of our STL journey. Today we are exploring a very important container std list, which is STL's implementation of a doubly linked list. By the end of this session, you will be able to confidently insert, delete, and traverse element in a list, compare its performance with vectors, and most importantly, know when to use it in real-world development scenarios. So what exactly is std list? It's a doubly linked list that's part of the standard template library. Unlike vectors or arrays, it does not store elements in contiguous memory. This unique structure means that inserting or deleting elements anywhere in the list, even in the middle, is fast and efficient. But there's a trade-off. You can't use the bracket operator to access elements like you would do in a vector. There's no random access. You have to use iterators to move through it. Let's take a peek inside. A doubly linked list is made up of nodes. Each node contains three parts: the data itself, a pointer to the previous node, and a pointer to the next node. These nodes are chained together both forwards and backwards. Because of this setup, we can insert or delete elements at any known position in constant time. No shifting required, unlike vectors. Declaring and initializing a std list is quite straightforward. You can start with an empty list like std list int list1 or initialize it directly with values. Lists can also hold other types like std string, float, or even custom objects. The syntax remains consistent with other STL containers, which makes it beginner friendly. Let's go over some basic operations you will often use with lists. Pushback adds an element to the end. Push front adds to the front. Insert allows inserting at any position using an iterator. And popback or popfront removes element from the respective ends. It's important to note that insert and erase work with iterators, not indices. That's a major distinction from vectors. To go through a list, we primarily use iterators. We start from begin and move till end, dereferencing the iterator to access each element. Alternatively, we can use a range-based for loop, which is more concise and readable when we just need to access elements one by one. Both approaches are valid. Use whichever suits the context of your code. Beyond the basics, std list comes with several powerful built-in functions. Sort lets us sort the elements. Unique removes consecutive duplicates. Reverse reverses the list in place. And remove deletes all occurrences of a specific value. Another standout feature is merge, which merges two sorted lists into one. It's extremely useful in merge sort algorithms, merge sort like algorithms, or any merging workflows. Let's compare list and vector side by side. Random access. Vector wins because it requires big of one access time with indexing. List has none. Insertion and deletion in the middle. List wins constant time if you have the iterator. Cache performance. Vectors perform better thanks to contiguous memory. Memory overhead. Lists consume more memory due to the extra pointers in each node. So lists are great for frequent modifications, but vectors are better when you care about access speed and memory efficiency. So when should you actually use list? Use it when you have frequent insertions or deletions in the middle of your sequence. Use it when the order of elements matters and you don't need random access. Also, if vector reallocation is causing performance issues, a list might be a better alternative. But avoid it if you need fast indexed access or if you are working in a memory sensitive environment, because that extra pointer data does add up. Here are a few common mistakes developers make with list. Trying to access elements using list I. This will not work. Applying algorithms like sort from algorithm. These expect random access, which lists don't support. Forgetting to use iterators with functions like insert and erase leads to complication error, compilation errors, or runtime bugs. Understanding these limitations early on will save you from a lot of frustration later. Let's test your understanding with a few mini challenges. Write a function that reverses a list manually. Merge two pre-sorted lists using merge. Sort a list and remove duplicates using sort and unique. Create a list of strings and remove specific values. These will give you good hands-on practice and help solidify your understanding of list operations. To summarize, list is a doubly linked list offering efficient insertions and deletions. It's perfect for situations where data changes frequently in the middle of the sequence, but you sacrifice random access and incur extra memory usage because of the internal pointers. Choosing the right container depends on the task, and now you know exactly where a list fits in. Great job finishing day 9. Let's keep the momentum going. Hello and welcome back to our journey through the standard template library in C++. Today is day 10 and we are going to take a deep dive into one of the most fundamental and widely used data structures, the stack. We will explore how it works using the LIFO principle, learn about the std::: stack container adapter in STL, understand the operations it supports, and see how it leverages other containers like vectors and TQs under the hood. By the end of today's session, you will not only be comfortable using stacks in code, but also understand where and why to use them effectively. Here's what on our roadmap for today. First, we will understand what a stack is conceptually, how it behaves, and where the LIFO principle comes in. Then we will explore std::: stack in STL, its syntax, methods, and the containers it builds upon. We will walk through code examples, discuss time complexities, and analyze practical use cases. Toward the end, we will look at how to build a simple stack manually using vectors and TQs, cover common mistakes developers make, and finally wrap it up with hands-on practice problems and your homework for the day. Let's begin. So what exactly is a stack? A stack is a linear data structure that follows the last in, first out, or LIFO order of operations. Think of it like a stack of plates in your kitchen cabinet. The last plate you put on is the first one you take out. You can't remove a plate from the bottom without removing the ones above it. Similarly, in a stack, the last element pushed in is the first one that comes out. This simplicity makes stacks powerful for managing data in a controlled, predictable way. Let's talk more about LIFO, or last in first out. Imagine you are pushing integers onto a stack in the following order: 10, 20, and 30. The last element you inserted is 30. It's now on top. When you perform a pop, 30 is removed and the new top becomes 20. So the last value pushed in is always the first to come out. This behavior is extremely useful in programming, especially in scenarios like function calls, undo operations, and parsing expressions where you need to reverse or backtrack through elements. C++ makes it easy to use stacks through its STL, the standard template library, with the std::: stack class. It's defined in the stack header and is what we call a container adapter. This means that it does not store elements on its own. Instead, it adapts existing containers like TQ, vector, or list. By default, it uses TQ. The stack interface gives us just what we need for a LIFO structure: push, pop, top, empty, and size. Nothing more, nothing less. It's a focused tool for focused use cases. Let's look at the core functions std::: stack provides. First, push adds an element to the top of the stack. Pop removes the element at the top, and note it does not return it. So you will want to call top beforehand if you need to access it. Top lets you pick at the element on top without removing it. Empty checks if the stack has no elements, and size returns how many elements are currently in the stack. These operations give us all the control we need to work within the LIFO paradigm efficiently. Here's a short code example that demonstrates stack operations. We create a stack of integers, then push two values onto it, 10 and 20. When we call top, it returns 20, the most recently added element. Then we pop the stack removing 20 and now top returns 10. This simple sequence clearly shows how the LIFO mechanism plays out in real time. You will be using this behavior frequently in algorithms and logic-heavy applications. One interesting thing about std: stack is that it does not function alone. It wraps around another container. This is what makes it a container adapter. By default, it uses a DQ because DQs offer efficient insertions and deletions from both ends. However, you can also use a vector or a list if your use case demands it. For example, if you don't need frequent pops but want tight memory allocation, vector may be ideal. When performance tuning, the choice of underlying container can make a significant difference. Time to talk about performance. All core stack operations push, pop, top, empty, and size are constant time or big of 1. This means that no matter how many elements are in the stack, each of these operations will complete in the same time. This predictability and speed are a big reason why stacks are a go-to structure in both real-time applications and algorithm design. Stacks are everywhere in the programming world. Think about the undo feature in a text editor. Every change you make is pushed onto a stack. When you hit undo, the topmost change is popped. They are also used for parsing expressions in compilers, balancing symbols like brackets and parentheses before performing depth-first search in graphs and managing recursive calls. Understanding stacks is like having a Swiss Army knife in your algorithm toolkit. While STL gives us a ready-made stack, understanding how to build one manually depends our grasp. Here we implement the stack using a vector. The push operation becomes pushback, pop becomes popback, and top becomes back. This version behaves just like an STL stack but gives us more control and transparency, perfect for debugging, customizing, or learning purposes. Now let's do the same thing but with a DQ. The logic is almost identical, but under the hood a DQ offers more flexibility in insertion and deletion at both ends. This version might be more performant in some cases where bidirectional access is useful. Again, pushback, popback, and back mirror the standard stack operations. Knowing how to switch containers like this will help you tailor your solution to the problem at hand. Even a simple data structure like a stack can trip you up. A common mistake is trying to access the top element or pop an element when the stack is empty. This leads to undefined behavior or crashes. Always check with memory with empty first. Also remember that stack does not support iterators or random access. You can't loop through it directly or access the third element. It's strictly top-only access. Keep these limitations in mind when designing your logic. Time to get your hands dirty. Here are some problems to reinforce your understanding. Try checking if parentheses are balanced in a string, a classic stack problem. Reverse a string using a stack, perfect for mastering push and pop. Convert an infix expression to postfix. This will challenge your logic and operator handling. And try simulating an undo system with two stacks. This one's fun and practical. These exercises are designed to stretch your understanding and improve your problem-solving skills. Let's summarize what we learned today. A stack is a linear data structure based on LIFO, last in first out. The stack class in STL provides a clean interface for stack operations and relies on other containers like DQ or vector to do the heavy lifting. We explored its methods, looked at manual implementations, discussed time complexities, and saw how stacks are used in the real world, from text editors to graph traversal. Stacks may be simple, but they are profoundly useful. Here's your assignment for today. First, solve the valid parenthesis problem on LeetCode. It's a textbook example of stack application. Then implement your own stack class using both vector and DQ to really understand the internals. Finally, take some time to read about how the call stack works during recursion. This is a foundational computer science concept that connects beautifully with what we learned today. You are now equipped with the knowledge, let's put it into action. Welcome to day 11 of our comprehensive STL course. In today's session, we will dive into one of the most fundamental yet powerful data structures, the queue. We will explore how the queue adheres to the first in first out principle, commonly known as FIFO, and how the C++ standard template library provides us with a robust and efficient queue implementation. By the end of this lesson, you will be confident in using queues to solve real-world and competitive programming problems. So let's get started. Let's begin by understanding what a queue actually is. A queue is a linear data structure that maintains the order of elements based on the first in first out model. This means that the first element inserted into the queue is the first one to be removed, just like waiting in line at a store or a service counter. You can only add new elements at the back and only remove them from the front. In real-world applications, queues are everywhere, from managing customers waiting in the line to buffering tasks in print queues to scheduling processes in operating systems. The queue enforces fairness by ensuring that requests are served in the order they arrive. To visualize the concept better, think about a real-life queue, like a line at a ticket counter. People join from the back and the counter serves the person at the front. There's no skipping and no random access, just a clean and fair process. This is exactly how a queue works in computer science. Understanding this analogy helps us relate abstract concepts to everyday experiences, which makes it easier to remember and implement them correctly. In C++, the standard template library gives us a ready-to-use queue container. To use it, we simply include the queue header. The std::: queue is implemented as a container adapter, meaning it wraps around another container, typically DQ or list, and restricts access to only the operations allowed in a queue. This abstraction allows us to focus on the queue's behavior rather than worrying about how it's implemented internally. And since it's built on top of efficient containers, performance is generally very good for typical use cases. Let's now look at the key functions provided by std::: queue. Push is used to insert an element at the back of the queue. Pop removes the front element, the one that was inserted first. Front returns a reference to the element at the front. Back gives you access to the most recently added element. Empty checks if the queue is currently empty, and size returns number of elements in the queue. These 6 functions are all you need to perform typical queue operations: insert, remove, check status, and access the ends. Now you might be wondering what data structure actually holds the elements inside a queue. Well, by default, queue uses DQ, which stands for doubly-ended queue, as its underlying container. A DQ supports fast insertion and removal from both ends, making it ideal for implementing a queue. However, STL also allows you to change the underlying container. For example, you could use a list instead, if that fits your needs better. The only requirement is that the container must support pushback, pop front, and access to both front and back elements. This gives you some flexibility depending on performance or memory considerations. Let's take a look at a simple code snippet to see how a queue works in practice. We declare a queue of strings and push two names, Alice and Bob. When you call Bob, Alice is removed from the front, so now we access front, we get Bob, who is next in line. This short example clearly demonstrates the FIFO behavior. The first person in is the first one served. Such usage is common in simulations, task dispatchers, and real-time systems. While the queue is a very useful structure, it's important to understand its limitations. First, You cannot randomly access elements inside a queue. Unlike vectors or arrays, there's no bracket operator or .add method. You can't jump to the third element, you only interact with the front and back. Second, there's no support for iterators. This means you can't loop through the elements of a queue using range-based for loops or iterators. These restrictions are by design. A queue is meant to be a strict FIFO structure, and allowing access to the middle would break that model. So where are queues used in practice? One major use is in breadth-first search, a graph traversal algorithm that explores nodes level by level. BFS relies on queues to ensure nodes are visited in the correct order. Job scheduling systems use queues to process tasks in order of arrival, ensuring fairness and predictability. Customer service applications use queues to store and serve support tickets. Any system where order and fairness matter is a potential use case for a queue. It's time to get your hands dirty with a small coding challenge. Create a queue-based container service system. Ask the user to enter customer names one by one. When they type exit, stop taking input. Then serve the customers in the same order they arrived by using pop and show the name of the customer currently being served using front. This is a great way to reinforce how queues manage and serve data in a fair and ordered manner. Let's take a moment to review with a quick quiz. First, what is the default container used by queue? Second, can you iterate through a queue like you can with a vector? And finally, what are the time complexities of push and pop in a queue? Pause here, reflect on these questions, and if needed, revisit the slides. These checks help ensure you are grasping the key takeaways. To wrap up, queues are essential structures for ordered processing. STL's std::queue offers a clean and efficient interface for FIFO operations. It uses a DQ by default but supports other containers like list. You have learned the core functions, seen a live example, and explored real-world applications from graphs to customer queues. While queues are limited in terms of access and iteration, they shine wherever order and fairness are required. In the next session, we will explore priority queues where elements are served not just by order of arrival but based on priority. Until then, keep practicing and happy coding. Welcome back to our STL journey. This is day 12 and today's focus is on one of the most powerful data structures for solving problems where priority matters, the priority queue. Whether you are dealing with scheduling systems, graph algorithms, or anytime elements need to be processed by importance rather than arrival time, the priority queue is your tool of choice. We will understand how it works, how to use it for both max and min heaps, and how to tailor it with custom comparators for advanced use cases. A priority queue is just like a regular queue, with one key difference. Instead of serving elements in the order they arrive, it always serves the element with the highest priority first. That means the element with the largest value or smallest, depending on how you define priority, comes out first. Think of it like an emergency room. Patients are treated by arrival time, but by how critical their condition is. Behind the scenes, STL implements this using a binary heap, which is a complete binary tree structure optimized for such optimizations. In C++, the priority queue is provided as a container adapter inside the queue header. This means it wraps around another container, typically a vector, and modifies its behavior to prioritize certain elements. By default, it works as a max heap, so the largest element is always accessible at the top. This is done using the less t comparator, which gives precedence to higher values. All you need to do is declare a priority queue int and start pushing elements into it. The heap property is maintained automatically. Let's look at a basic example. We declare a priority queue int and push three values 10, 20, and 5. The queue automatically arranges them so that the largest element, in this case 20, is at the top. When we call top, we get 20. After popping it, 10 becomes the new top. The priority queue ensures that each time you pop an element, the next largest one is promoted to the top. This is the default max heap behavior, simple yet powerful. Now, what if we want the smallest element to come out first? This is where mean heaps come into play. By default, priority queue does not support mean heap behavior, but we can achieve it easily using a comparator. We define the queue with three template parameters: the type of the elements, underlying container, and the comparator. By passing greater int as the comparator, we flip the default behavior. Now the smallest element always rises on the top. This is particularly useful in algorithms like Dijkstra's shortest path, where we want to always process the nearest node next. Let's quickly go over the performance. Accessing the top element, the highest or lowest priority, is a constant time operation. That's because the top of the heap is always at the root. Pushing a new element or popping the top element both take log n time, where n is the number of elements in the queue. That this logarithmic time comes from the need to maintain the heap structure through upheaping or downheaping. These efficient operations make priority queue a highly effective tool for real-time and large-scale computations. Sometimes you will work with more complex data like structs or pairs where the default comparison isn't enough. That's where custom comparators shine. A comparator is simply a callable object, typically a struct with an overloaded operator. This function takes two elements and returns true or false based on your custom priority rules. You might want to prioritize by deadlines, scores, weights, anything. By injecting your logic into a comparator, you gain full control over how elements are ordered in the queue. Here's a real-world scenario. Let's say we are working with a list of tasks, each represented as a pair of integers, task ID and priority. We want our priority queues to order tasks based on their second value, the priority. Using a custom comparator, we define the ordering logic and STL takes care of the rest. Now when you insert task into the queue, they will automatically be sorted based on how urgent they are. This is a foundational skill for coding interviews and advanced problem solving. Before we move on, let's talk about some common mistakes. First, forgetting to use greater for a mean heap. This will silently give you the wrong behavior. Second, calling pop before top. Remember, pop removes the top element, but it does not return it. So if you forget to call top first, you lose that data. Third, confusing priority queue with queue or stack. A queue works in FIFO order, a stack in LIFO, but a priority queue is based entirely on value-based ordering. Always keep that difference in mind. To solidify your understanding, try applying priority queue in practical problems. Start with the classic, find the top k largest or smallest elements in an array, a great way to get comfortable with heap usage. Then move on to something more dynamic like finding the median in a stream of numbers, which requires two heaps. Finally, attempt merging k-sorted arrays, a common use case where a mean heap shines. These problems will not only build your STL skills but also prepare you for real coding interviews. The priority queue isn't just a classroom concept, it's used everywhere. In operating systems, it manages process scheduling so that high priority tasks run first. In network routing, it ensures critical data packets are transmitted with priority. In graph algorithms like Dijkstra's or Twins, it ensures the most optimal node is always processed next. Even in AI simulations or event-driven systems, it handles the sequence of events based on time or urgency. Mastering these tools equip you to build systems that are fast, responsive, and smart. To wrap up today's session, here's your homework. First, solve two lead code problems that require priority queue. This will give you a chance to practice both max and mean heaps in real problems. Next, simulate an emergency room queue where patients are treated based on severity. Use custom comparators here. And for those of you seeking an extra challenge, Design a toggleable priority queue, one that can switch between min heap and max heap modes at runtime. These exercises will push your understanding and make sure you truly own this concept. Welcome to day 13 of our STL course. Today is entirely focused on practicing what we have learned. We will reinforce the fundamentals of stacks and queues through hands-on coding problems. Our goal is to sharpen your ability to think algorithmically using STL. We have curated 4 stack problems and 4 queue problems, each covering different patterns and levels of difficulty. We will also discuss debugging methods, analyze time complexities, and walk through efficient solutions. Let's dive into this problem-solving adventure. Before we dive into coding, let's quickly refresh our understanding of stacks and queues. Stacks follow a last-in, first-out pattern, ideal for problems where the most recent element needs to be accessed first. Think function calls or undo operations. Operations like push, pop, and top are key. Queues, on the other hand, are first in, first out, used when order matters, like scheduling or buffering. Both are backed by efficient containers like DQ and offer constant time complexity for most operations, making them perfect for real-time tasks. This is a classic problem often asked in interviews. The challenge is to validate whether a string of brackets is correctly nested and closed. We use a stack to store opening brackets as we encounter them. When a closing bracket appears, we check if it matches the top of the stack. If at any point it does not, or if the stack isn't empty at the end, the string is invalid. This is a great demonstration of stack behavior in parsing problems. In this problem, you are asked to find the next greater number for each element in an array. A naive approach is big of and square, but using a monotonic stack, we can reduce it to linear time. The idea is to keep a stack of elements in decreasing order. As we move when conditions are met, this efficient stack problem is common in many optimization scenarios. This one's a twist on the regular stack. Alongside standard stack operations, we need to retrieve the minimum element in constant time. The trick: use a second stack to track minimum values. Every time you push, compare it with the current min and update accordingly. When you pop, remove from both stacks. This dual stack setup is a great way to enhance basic data structures with additional features. Here we evaluate expressions written in reverse Polish notation, where operations follow their operands. This means no parentheses and no precedence confusion. We use a stack to store numbers. When an operator is encountered, we pop the last two numbers, apply the operation, and push the result back. It's a great example of how stacks are used in interpreters, compilers, and calculators. This problem simulates a live stream of characters where you need to identify the first non-repeating character at every point. We use a queue to maintain the order of characters and a hash map to track frequencies. As we iterate, we remove characters from the front of the queue if their count exceeds 1. This problem teaches us how queues are ideal for maintaining order under dynamic conditions. In this design challenge, we implement a circular queue that wraps around once it reaches the end. We manage it using a fixed size vector and pointers for the front and rear. This structure is used in buffering data, task scheduling, and memory-limited environments. It's a practical application of queues in systems programming and shows the real-world importance of efficient container design. This is a high-frequency interview question. You are given an array and a window size, and you need to return the maximum element in each sliding window. A brute force approach works but isn't optimal. Instead, we use a DQ to store indices in a way that ensures the front always contains the current maximum. As the window slides, we remove out of window elements and maintain decreasing order. This highlights how queues can drastically improve performance in sliding window scenarios. This grid-based problem simulates how rot spreads among oranges over time. Each minute, broken oranges infect adjacent fresh ones. We use a queue to implement a breadth-first search, treating each minute as a level in the BFS tree. By counting the levels, we calculate the total time to rot all fresh oranges. If we can't reach some fresh oranges, we return -1. This problem is a strong example of BFS in metric-based traversal. When debugging stack or queue problems, visualization is key. Use print statements to track changes in your container. Watch for off by one errors, especially when dealing with indices and loops. Also, don't ignore space complexities. Optimize memory where possible. Prefer DQ over list in most STL contexts due to better performance. And always consider edge cases. They often reveal hidden bugs and edge logic. Great job for today. To reinforce what we have learned, try solving at least 6 of the 8 problems. Push your solutions to GitHub. It not only tracks your progress but also builds your portfolio. Revisit STL documentation for stack and queue if you need a refresher. And for those who want an extra challenge, try implementing a stack using a list container from scratch. Keep coding and see you in the next session. Welcome to day 14 and congratulations on completing week 2 of your STL journey. You have now covered 5 essential containers: DQ, list, stack, queue, and priority queue. Each of these plays a crucial role in real-world problem solving. Today is about revisiting what we have learned, reinforcing the key concepts, and testing your knowledge through an interactive quiz. The goal here is not just to memorize, but to deepen your understanding and build confidence as we move into more complex STL containers in week 3. Let's dive in. Let's start with the DQ, short for doubly ended queue. What makes it unique is that it allows you to insert and remove elements from both the front and the back. This gives it a performance advantage in many scenarios where both ends of a sequence need to be accessed efficiently. Under the hood, a DQ uses a segmented dynamic array. This means it does not reallocate memory as frequently as a vector when resizing, especially at the front. You will often see DQ used in problems like the sliding window maximum, where you need quick front and back operations. Think of it as a flexible and efficient alternative to vectors when two-end access is required. Next up, we have the STL list, specifically a doubly linked list. Unlike vectors and DQs that use contiguous memory, a list is made of nodes that are spread out in memory and connected through pointers. This structure allows for extremely efficient insertions and deletions, especially in the middle of the list, something that vectors and DQs can't do efficiently. However, there's a trade-off. Since the elements aren't stored in a contiguous block, you can't access them randomly with square brackets. You have to traverse the list using iterators. Use lists when your operations involve frequent modifications, especially in the middle of the sequence, and not when you need fast access by index. Now let's review the stack, a classic last in first out or LIFO structure. This container is extremely useful in problems that require backtracking, recursion simulation, or tracking nested structures like brackets or function calls. The key functions are push to insert, pop to remove, and top to view the last inserted elements. Internally, a stack can be implemented using a vector, DQ, or even a list, but it restricts access to only one end, the top, so you can't iterate or access other elements directly. If you need to examine elements, you will have to pop them off one by one. Think of it as a controlled access container that mirrors real-world stack behavior. Let's cover two more containers, queue and priority queue. A queue is a first in first out or FIFO structure, just like a line at a store. You insert at the back with push and remove from the front with pop. It's ideal for task scheduling, process management, and breadth first search. On the other hand, a priority queue is a container that always gives access to the element with the highest priority. By default, it behaves like a maxip, meaning the largest element is always at the top. But with a custom comparator, you can turn it into a mean heap, useful for Dijkstra's algorithm or when you need the smallest element. Internally, a priority queue is backed by a vector and uses heap algorithms to maintain order. Now let's look at some common mistakes students often make when working with these containers. First, never access the top of a stack or the front of a queue without first checking if the container is empty. Doing so could lead to crashes or undefined behavior. Next, remember that list does not support square bracket access. It's not an array. Another common misconception is thinking that a priority queue is fully sorted. It's not. Only the top element is guaranteed to be the highest priority. The rest are in heap order. Finally, it's easy to confuse front and back when working with DQs, especially when popping elements from both ends. Watch out for this. They can trip you up during coding or interviews. Alright, it's time to challenge yourself with a quiz. This one has 10 questions that mix theory and practice. There are 5 multiple choice questions to test your conceptual clarity, 3 output based questions where you will predict what a piece of code will produce, and 2 debug the code problems that require spotting and fixing logical or syntax issues. Take your time, pause the video if needed, and really try to solve them before checking the answers. This is your checkpoint to ensure you are truly grasping what we have covered. Let's go through the quiz together. For each question, I will give you the correct answer and explain the reason behind it. This isn't just about being right or wrong, it's about learning why. We will also highlight common mistakes and clear up any misconceptions. These explanations will strengthen your conceptual foundation and prepare you better for real-world coding, interviews, and contests. Looking ahead to week 3, we are entering the world of associative containers. This includes sets and maps, both in ordered and unordered forms. You will learn how to store key value pairs before lookups in constant time. Even customize how elements are compared using custom comparators. We will also take a deep dive into iterators, a critical topic that empowers you to traverse containers effectively. Week 3 also includes a mid-course quiz to evaluate your learning progress. It's going to be an exciting and intellectually rewarding week. You have done a phenomenal job completing week 2. These containers you have studied from the foundation of efficient problem solving in C++. Remember, mastery isn't about rushing. It comes from repeating, reflection, and application. So keep practicing, code daily, review what you have learned, and tackle real problems from platforms like LeetCode or Codeforces. And most importantly, stay curious and don't be afraid to ask questions. You are building a strong code toolkit that will serve you throughout your software development journey. Let's keep going and make week 3 even more awesome. Welcome back to our STL journey. Today marks day 15 and we are diving into an essential part of the STL, the set container. Sets are perfect when your goal is to manage collections of unique values and you want either fast access or sorted ordering. Throughout today's session, we will explore the two major variants, the ordered set and the unordered set. You will learn how they work, when to use which, and how to apply them in practical programming situations. By the end of this lesson, you will have a clear understanding of how both set and unordered set work. We will cover syntax, internal implementations, operations like insertion, deletion, and searching, and the performance characteristics that differentiate them. You will also write some code, analyze time complexities, and try out coding exercises that simulate real-world use cases. The goal is to help you make an informed decision about which type of set to use depending on your needs. A set in STL is a container that stores only unique elements. That's the key idea. If you try to insert a duplicate, it will be silently rejected. The main use of a set is when you want to filter out duplicates, search efficiently, or maintain a sorted structure. There are two kinds: the ordered set, which automatically keeps its elements in sorted order using a red-black tree, and the unordered set, which uses a hash table and provides constant time average access. We will be focusing on both in this session. Let's start with set, the ordered version. This is implemented internally as a red-black tree, a type of self-balancing binary tree. That means elements are always kept in sorted order and all operations insert, erase, and search run in log n time. You can think of set as a sorted list that does not allow duplicates and allows fast lookup. It's best when ordering matters, like when building a leaderboard or sorting a set of names automatically. Here we see some operations for std::: set. First, we declare a set of integers. When inserting values, any duplicates are silently ignored. Try inserting 10 twice and you will see it only appears once. Searching is done using the find function, which returns an iterator. If it matches the end iterator, the element wasn't found. Deleting is as simple as passing the value to the erase function. All of these operations are fast and reliable, and due to the tree structure, elements are automatically ordered. Now let's shift our focus to unordered sets. This container has the same property of uniqueness, but is not ordered. Internally, it uses a hash table, which gives us average case of week of 1 performance for insertions, deletions, and lookups. However, since it uses hashing, the elements do not maintain any specific order. It's great when you care about speed and not about ordering. For example, checking if a user has already logged in or if a word has already been processed in a large text. In this example, we create an unordered set of strings and insert several values, including a duplicate. Notice how apple only appears once. We can use find to search for specific entries. The lack of order might look odd at first, but the performance gains are significant. This makes unordered set an ideal choice when you are dealing with large data and just need fast, reliable lookups like checking if a number has already appeared in the string. This table helps summarize the core differences. In terms of internal structure, set uses a balanced tree while unordered set uses a hash table. That means set provides log n time complexity and unordered set gives constant on average. The trade-off is that set maintains order while unordered set does not. Use set when order matters or when you need predictable traversal. Use unordered set when you just care about speed and don't need ordering. Both reject duplicates, but the underlying behavior is quite different. When should you use sets in real applications? Use set for leaderboards, ranking systems, event timelines, or anywhere you need sorted unique elements. On the other hand, use unordered set for fast filtering, checking presence of elements, or removing duplicates from large datasets. For instance, if you are analyzing user activity logs and want to know how many unique users visited a page, unordered set is the way to go. Here's a quick practical task. Suppose you have a vector with repeated integers. How do you remove duplicates? Simply pass the vector elements into a set using an iterator range. This instantly filters out all duplicates. If you care about performance, use unordered set. If you want the results in sorted order, go for set. You can even convert the set back to a vector if you need array style access later. This next exercise simulates a real-world use case, text analytics. Given a paragraph of text, you want to count the number of unique words. Step 1. Break the text into words using a string stream. Insert each word into an unordered set. Return the size of the set. This simple pattern powers everything from spam filters to keyword extractors. Just try it out. Let's run a quick performance comparison. We generate a large list of random numbers and measure the time taken to insert and search in both set and unordered set. You will usually find that unordered set is significantly faster, except in rare cases where hash collisions degrade its performance. Meanwhile, set offers more consistent behavior and predictable iteration. These benchmarks help you decide which container to use based on context. Here are some key tips. First, once an element is inserted into a set, you cannot modify it directly because doing so might break the internal ordering or hashing. You will need to remove and reinsert. Second, if you use custom data types in an unordered set, you must define a custom hashed function. Lastly, don't assume one is always better than the other. Profile and choose based on your application's need. Time to get hands-on. Here are some practice problems for you. Remove duplicates from an array using a set. Count distinct elements in multiple arrays. Check if two strings have the same set of characters. Find the intersection of two arrays using sets. These problems will give you strong muscle memory with set containers. Try them on LeetCode, HackerRank, or CodeForces. On day 16, we are going to level up. We will look at multisets which allow duplicate values. They are great when you want to count the frequency of elements while keeping them sorted. We will also compare them to sets and see where each fits best. See you in the next session where we go one level deeper in mastering STL containers. Welcome to day 16 of our journey through the C++ standard template library. Today we explore a very interesting and often underutilized container, the multiset. Unlike the set container, which strictly disallows duplicate values, a multiset permits duplicates, making it ideal for cases where repeated values are significant. Just like set, all elements remain sorted by default in ascending order, and this property is maintained internally using a red-back tree, which is a type of self-balancing binary tree. This structure ensures that operations like insertion, deletion, and search are always efficient regardless of the number of elements. A multiset is categorized as an associative container in the STL. The term associative means that elements are sorted and accessed based on their values rather than positions or indices. What makes a multiset unique is its ability to store duplicate values. Multiple elements with the same value can coexist. Additionally, the container automatically maintains a sorted order, so you never have to manually sort the data after inserting elements. The internal mechanisms of the multiset are designed to offer fast access for searching, inserting, and deleting elements, all with a time complexity of log n due to the underlying balanced tree. Creating a multiset in C++ is very straightforward and feels just like declaring a regular set. For instance, you can write multiset int ms to create a multiset of integers, or multiset string names for sorting strings. This container is highly versatile. It supports user-defined types as well, provided you define how elements should be compared, usually through overloading the comparison operator or by passing a comparator. This makes multiset a powerful option in real-world coding scenarios where duplicates and sorting matters. Inserting values into a multiset is similar to other STL containers. You simply call the insert function. Here the key point. Unlike set, the multiset allows you to insert the same value multiple times. In this example, 10 is inserted twice, and that's completely valid. Internally, the red-back tree structure adjusts itself to ensure that the values remain sorted after each insertion. So no matter how many duplicates you add, the order is always preserved automatically. Now let's talk about deleting elements from a multiset. If you use ms.erase10, it will remove all instances of the value 10 from the container, so be careful when using this. But what if you want to remove only one occurrence of a value that appears multiple times? For that, you can use an iterator. First use find to locate the value and then pass the iterator to erase. This approach gives you fine-grained control over the deletion process, which is crucial when working with repeated values. The multiset offers handy functions like count and find to work with its contents. The count function tells you how many times a particular value appears in the multiset. This is especially useful when you are analyzing frequencies or validating duplicates. The find function returns an iterator at the first occurrence of a given value. If the value does not exist, it returns ms.end. This is particularly useful when you are looking to perform operations on specific entries. Iterating through a multiset is both simple and powerful. Using a range-based for loop, you can visit each element in sorted order, and yes, that includes duplicates. So if you have inserted the number 10 three times, you will see it 3 times during iteration, appearing in their proper sorted position. This property makes the multiset ideal for outputting or analyzing ordered data with repetitions such as logs, scores, or events. By default, multiset sorts elements in ascending order, but what if you need the largest elements first? That's where custom comparators come in. By passing greater in as the second template argument, you can create a multiset that sorts elements in descending order. This is extremely useful in applications like leaderboards, priority systems, or anywhere you need to track and display the top values first. Let's compare set and multiset side by side. First and foremost, sets do not allow duplicates, while multisets do. In terms of performance, both offer logarithmic time for insertion and lookup due to their tree-based structures, and both maintain sorted order. So the main deciding factor is whether your use case requires duplicate handling. If yes, multiset is the clear winner. Let's explore where multisets shine in real-world applications. You can use them to store game or exam scores where multiple players might have the same score. They are excellent for word frequency analysis, where each word's occurrence is counted. They help manage timestamps and event collisions, particularly in logging systems. And finally, they are useful in frequency counters when you want to build one quickly without using a hash map. Let's look at the internal complexity of multi-set operations. Insertion, deletion, and search all have a time complexity of log n thanks to the self-balancing red-black tree. Iterating through the multiset takes n time since you are simply walking through each element in sorted order. This consistent performance, regardless of data size, is a major strength of tree-based containers like multiset. Let's bring it all together with a quick hands-on example. First, take a list of numbers from user input or a file. Insert these numbers into a multiset and remember, duplicates are welcome. Next, use count to find how many times a value appears. Finally, practice erasing both all occurrences of a value and just a single instance. This hands-on session will solidify your understanding of multiset behavior. There's a practical use case, an exam score tracker. Students often take multiple tests and we need to store all their scores. A multiset is perfect for this because it allows repeated scores while keeping them sorted. You can easily retrieve the top few scores using a descending multiset or remove a specific score if a re-evaluation occurs. It's clean, efficient, and gets the job done without extra logic. Let's summarize today's key points. The multiset container allows you to store duplicate elements while maintaining them in sorted order. It is built on black-black tree, which guarantees logarithmic time complexity for core operations. Insertion, deletion, and search are straightforward, and you can use custom comparators to tweak the ordering. All of these features make multiset an ideal choice for applications that are sensitive to duplicates and order. To reinforce today's learning, here are a few practice problems. First, try inserting values with duplicates into a multiset and use count to track how many times each appears. Next, implement logic to erase only one instance of a duplicate value. Finally, use a descending multiset to store a list of scores and retrieve the top 3 highest values. These problems will help you gain practical mastery of the multiset container. Welcome to day 17 of our journey into the standard template library. Today we are focusing on one of the most powerful and widely used containers, the map. Whether it's an ordered map or an unordered map, this data structure forms the backbone of many real-world applications like indexing, counting, and searching efficiently. We will also explore how key-value pairs work using pair and see how maps give us flexibility and speed in storing and retrieving data. Let's dive in. A map in STL is an associative container that stores elements in key-value pairs. Each key must be unique and it maps to exactly one value. There are two main types: an ordered map, simply called map, which maintains its elements in sorted order by key; an unordered map, which uses hashing for fast lookups and does not maintain any specific order. Internally, map is implemented using a red flag tree, giving us logarithmic or log n time complexity for insertions, deletions, and searches. On the other hand, unordered map uses a hash table, giving us average constant time for the same operations. However, in worst case scenarios like hash collisions, it can degrade to n. This makes understanding the internal implementation important when choosing between the two. Let's look at how to declare maps. We can declare an ordered map like std::: map int, string, id to name. Here each integer key maps to a string value, perhaps an id mapped to a person's name. For faster access, we use std::: unordered map string, int, word count. This would be great for counting word occurrences. Remember, map keeps keys sorted while unordered offers no guaranteed order. Make sure to include the correct headers: map for ordered maps and unordered map for unordered ones. There are multiple ways to insert data into a map. The simplest way is using the subscript operator, m key assigned value. If key does not exist, this creates a new entry. If it does, it updates the existing value. You can also insert using m.insert key, value, or even better, use mplace for efficiency. m.mplace key, value. Why is mplace better? Because it constructs the pair in place, avoiding a copy or more. A key point to remember: maps don't allow duplicate keys. Inserting the same key again will override the existing value. When you access elements using the subscript operator like this, m key, you need to be careful. If the key isn't present, the map will automatically insert it with a default value. That's not always what you want, especially if you are just checking for existence. A safer way is to use m.add key. This throws an exception if the key isn't found, avoiding unintended insertions. The most robust approach, use find. This allows you to check if a key exists before using it. You can traverse a map using a range-based for loop or iterators. Each element in a map is a pair where dot first refers to the key and dot second refers to the key value. Here P is a reference to each pair const key, value. You can also destructure the pair directly. This makes your code cleaner and more readable. Here's a side-by-side comparison of map and unordered map. Use map when you need keys sorted or want predictable traversal order. Use unordered map for placing fast insertions and lookups, provided your keys are hashable and you don't care about order. Each element in the map is essentially a pair const key, value. Understanding how pairs work is essential for using maps effectively. You access the components with dot first and dot second. Using structured bindings makes it even easier. This way, your loop variables directly hold the key and value, making code more readable and concise. Maps are mutable. You can modify their contents easily. To remove an element like key, use m.erase key. To clear all element, use m.clear. To check for existence without inserting, use m.find key. It returns an iterator to the key if found or m.end if not. Let's walk through a real-world example counting word frequency. Here each word is read from input and its count is incremented. Why unordered map this time? Because it gives us constant time insertions and lookups, making it perfect for counting, indexing, and grouping data efficiently. There are a few common pitfalls when working with maps. Using M key on a missing key inserts it, sometimes unintentionally. Unordered map does not work well with custom classes or complex types unless you provide a hash function. Iteration order in unordered map is not guaranteed, so never rely on it for ordered output. Be mindful of these quirks when choosing and using map containers. Let's put your knowledge to the test with some practice problems. Count the frequency of each character in a string. Map roll numbers to student names. Count the number of distinct integers in a vector. Store and update the last seen index of elements in an array. These problems will give you hands-on experience with insertion, lookup, and traversal of maps. It's quiz time. Let's see how much you have picked up. What's the difference between using m key and m.add key? Can you map contain duplicate keys? What the average time complexity of an unordered map operation? When does an unordered map degrade to n complexity? These are key questions to assess both your conceptual clarity and practical readiness. To summarize, use map when sorted order of keys matters. Use unordered map when performance is the priority and order does not matter. Understand how to access key value pairs via dot first and dot second. And always be cautious of inserting values silently. It can lead to hard to find bugs. Maps are a core part of STL and mastering them opens doors to writing clean, efficient code in C++. Great job, see you in the next session. Hello and welcome back to our in-depth journey through the STL. This is day 18 and today we are focusing on a container that often files under the radar but is incredibly useful in the right situations. It is the multi-map. We will look at how it works, when to use it, how it compares to similar containers like map and unordered map, and explore some practical real-world applications. So if you have ever wondered how to handle duplicate keys in STL, this is the session for you. Let's begin by understanding what a multi-map actually is. At its core, a multi-map is an associative container, which means it stores elements in the form of key value pairs just like a map. But here's the big difference. Unlike map, which only allows unique keys, a multi-map can store multiple elements with the same key. This makes it ideal when a one-to-one or one-to-many relationship exists in your data model. For example, think of a dictionary where one word has multiple definitions or a student receiving multiple grades. It's included in the map header, and just like map, it keeps its elements sorted by key. Internally, it's powered by a red-black tree which ensures the insertions, deletions, and lookups happen in logarithmic time, so it's both elegant and efficient. Let's now look at the syntax. Declaring a multi-map is as simple as including the map header and using the multi-map keyword. Here we have defined a multi-map where each key is a string representing a student's name and each value is an int representing their score. Take note of these insertions. We insert Alice with a score of 90, Bob with 85 and Alice again with 95. This is perfectly valid in multi-map. It does not overwrite the earlier Alice entry like a map would. Instead, it keeps both, and the container ensures that keys are kept in sorted order, so Alice entries will appear before Bob in this case. When it comes to inserting elements into a multi-map, we have several flexible options. First, we can use the insert function with a pair to take advantage of C++11's initializer list syntax, like we saw earlier. If you have a range of elements, say from another container, you can use range insertion mmp.insert start, end. A key highlight: since multi-maps allow duplicate keys, every insertion is preserved. Unlike map where adding a key that already exists would silently fail or override the value, multi-map welcomes duplicates. This makes it reliable for collecting grouped data. Now let's talk about how to access data in a multi-map. This is where things differ significantly from a map. A map allows you to use the square operator for quick access like m key, but a multi-map does not support this because square brackets assumes a one-to-one mapping of key to value. With multi-maps, we might have multiple values per key, so it requires a different approach. Instead, we use member functions like find key to get an iterator to the first matching key, lower bound and upper bound to define ranges, and most importantly, equal range. This gives us a pair of iterators representing the full range of values associated with a given key. In the code shown, we retrieve all scores for Alice using equal range, then loop through that range and print each score. This pattern is incredibly useful when handling grouped data. Just as important as inserting and accessing data is knowing how to erase it. With a multi-map, there are three main ways to remove elements. First, we can pass a key to erase to remove all elements that match that key. Second, you can erase an element by passing a specific iterator, perfect when you want to surgically remove just one occurrence. Third, we can erase a range of elements using two iterators. This fine-grained control is powerful, especially in applications where data is dynamic and changes frequently. So when should you actually use a multi-map in your applications? Here are a few real-world scenarios. Student grades. A student might have multiple scores over time. You want to group them by name but keep all scores. Word context mapping. Suppose you are building a text analyzer tool and you want to map each word to all the positions it appears in a document. That's a natural fit for a multi-map. Event scheduling. If you are building a calendar or scheduler, you might have multiple events occurring on the same day. You need to associate that single key, the date, with multiple values, the events. These examples show the versatility of multi-map when it comes to modeling real-world one-to-many relationships. Let's now compare multi-map to its close cousins map and unordered map. First, duplicate keys. Only multi-map allows them. Both map and unordered map enforce unique keys. Next, ordering. Map and multi-map maintain sorted order of keys thanks to their underlying red-black tree structure. Unordered map, on the other hand, uses a hash table, so the elements are stored in an unpredictable order. In terms of access, only map and unordered map support a bracket operator. Since multi-map can have many values per key, this syntax would not make sense. Finally, time complexity. For most operations like insert and lookup, map and multi-map offer log-n performance. Unordered map is generally faster with average case of constant time, but only when you don't care about ordering. This comparison is critical when choosing the right container for your problem. Alright, let's test what you have learned with a hands-on challenge. Your task is to write a program that stores and displays the scores of students. Remember, students can appear multiple times, so duplicate keys are expected. The input might look like this: Alice 90, Bob 85, Alice 95, and Bob 87. The output should group scores by student, so for Alice, you would print 90 and 95. Use equal range to retrieve all the values for each student. This is a perfect real-world use case where multi-map shines, grouping data efficiently and keeping it stored. Let's wrap up today's lesson with the key takeaways. Multimap is an STL container that allows multiple values for the same key. Unlike map, it does not support the bracket access operator, so we rely on find, equal range, and related methods. Internally, it maintains sorted order, just like map, making it useful for ordered traversals. Whenever your data follows a many-to-one relationship, like multiple grades per student or multiple events per date, multimap should be your go-to choice. Choosing the right container not only makes your code more efficient but also more intuitive to read and maintain. And that brings us to the end of today's session on multi-map. I hope you now see the power and flexibility that this container offers, especially when dealing with duplicate keys. If you have any questions or want to explore deeper use cases, feel free to ask. In the next session, we will look at how to customize sorting behavior using custom comparators in sets and maps, a feature that gives us even greater control over your data structure. So I will see you there. Hello and welcome to day 19 of our STL Mastery series. Today we are diving into an advanced but essential concept in C++ STL, custom comparators in sets and maps. This lesson will unlock a powerful layer of control over your containers and elevate your understanding of how data can be stored, accessed, and sorted efficiently and intuitively. So let's begin. Here's what you will take away from today's session. First, you will understand why default sorting isn't always enough and when custom comparators become necessary. Next, you will learn how to implement custom comparators using three primary approaches: functors, lambda functions, and operator overloading. And finally, we will see how these techniques are used in real-world applications like ranked lists, task schedulers, and leaderboards. By default, ordered containers like set and map use std::less, which sorts elements in ascending order. But what if you want descending order, or need to sort a complex object like a student by marks and then name, or organize employees by salary? These cases can't be handled with default behavior. That's when you define a custom comparator, giving you precise control over how elements are compared and stored. This is especially important in real-time systems, dashboards, and algorithm challenges. Let's start simple. The greater comparator is built into the STL and reverses the default sort order. In this example, we use set int greater int and the numbers are stored in descending order from largest to smallest. It's a handy shortcut when all you need is reverse sorting and you don't want to write custom code. Now let's go deeper. A functor is a class or struct that overloads the function called operator. In this example, the test functor compares two integers and returns true if the first is greater than the second, achieving descending order. Functors give you flexibility. You can keep internal state, reuse the logic, and even template them for multiple types. Functors are especially useful when dealing with user-defined types. Take this student struct. It contains an ID and a name. The default comparison won't know what to do with it. By creating a compare by ID functor, we define custom logic to sort students in their ID. Without this, the set would not know how to insert or arrange the students at all. Sometimes you don't need a full functor. You just need a quick comparison for a one-time use. Lambdas are perfect for this. Here we define a lambda that compares two pairs by their second value. Using take type and passing the lambda into a set, we achieve custom ordering in line. It's elegant, functional, and keeps code concise, especially for sorting collections of pairs or tuples. There are a few things to keep in mind when writing custom comparators. First, your comparison must follow strict weak ordering. This means it must be consistent and logical. Otherwise, the container's behavior becomes undefined. Second, remember that in maps only the keys are compared, not the values. Also, unordered containers like unordered map or unordered set don't use comparators. They rely on hash functions. Lastly, if your object already overloads, you may not even need a custom of comparator. Here's a realistic and very common use case. Sorting students first by their marks in descending order, and if the marks are equal, then alphabetically by their names. To achieve this, we define a student start and a comparator that first checks marks and only checks names if marks are tied. This compound logic is a classic pattern, and you will encounter it frequently in ranking systems, data dashboards, and competitive programming problems. Now let's put your knowledge to the test with a few mini tasks. Try creating a set that stores integers in descending order. Then define a map that uses a custom object as the key, stored by a specific property like name. Next, write a lambda comparator to sort a set of pairs. And finally, write a compound comparator that sorts based on two fields, like we saw in the last slide. These mini challenges will help reinforce your understanding. Custom comparators often show up in interviews. One common question is, how do you sort a map by value instead of key? This isn't directly supported, so you would extract the contents and sort them manually. Another question, how do you sort a set of structs? Here you would use custom comparator, just like we did with students. Finally, many candidates get tripped by unordered containers. Remember, they don't support custom comparators because they use hashing instead. To stretch your skills, here are some practice problems. Build a system that stores employees sorted by salary with a fallback sort on each, or create a live leaderboard where participants are ranked by sports and names. You could also design a data structure that automatically maintains the top n items using a custom rule. Each of these problems will challenge your comparator logic and sharpen your STL fluency. Here's a quick summary of what we have covered today. We explored the built-in creator comparator. We wrote functor-based comparators to sort integers and structs. We used lambda expressions to simplify custom logic inline. We handled stack comparisons and applied these concepts in real-world scenarios. Each of these tools gives us tighter control over our data structure. Before we wrap up, here's your homework for today. First, design a leaderboard using set or map, sorted by score in descending order and name in case of ties. Second, create a task manager where tasks are sorted by priority from high to low and for equal priority by earliest deadline. These tasks mimic real-world problems and will solidify your mastery of custom comparators. Welcome to day 20 of our STL course. Today we embark on a key topic in the STL ecosystem, iterators. These are the foundation of container traversal and a gateway to using STL algorithms effectively. In this session, we will dive into what iterators are, explore their different types like reverse iterators and const iterators, and even write a basic custom iterator. By the end of this lesson, you will not only understand how to navigate STL containers in multiple directions, but also how to do so safely and efficiently using iterator best practices. Let's get started. Let's take a look at today's learning objectives. By the end of this session, you will clearly understand what iterators are and why they are used in STL. You will learn how to use reverse and const iterators to handle different traversal scenarios. You will categorize iterators into types like forward, bidirectional, and random access. And finally, you will understand how to create a simple custom iterator, an essential skill for designing iterable classes. We will also discuss common pitfalls to avoid while using iterators, so you can write safer and cleaner C++ code. So what exactly is an iterator? In simple terms, an iterator is a generalized pointer. It acts like a pointer in that you can move it forward or backward and dereference it to access elements. But unlike raw pointers, iterators are safe type and container aware. meaning they know how to work with STL containers. They provide a common interface that allows us to traverse elements without knowing the container's internal structure. Thanks to iterators, algorithms like sort, find, accumulate, and many more can work with any container uniformly, whether it's a vector, set, or map. They truly embody the power of abstraction in STL. STL classifies iterator into 5 categories, each offering different capabilities. Let's go and explore them. Input iterators. These can read data as we move forward through a container. You can think of them like reading from a file or stream. Output iterators. These are used to write data, for instance, writing to an output stream or inserting into a container. Forward iterators. These support multiple passes in the forward direction, useful in singly linked lists. Bidirectional iterators. These can move both forward and backward. Think of list and set. They support bidirectional iteration. Random access iterators, the most powerful. They support direct jumping, like moving ahead by 3 positions instantly. Containers like vector and DQ support this. Understanding which type your container supports helps you choose the right algorithm and method for the job. Now let's explore constant iterators or const iterators. These iterators offer read-only access to the elements of a container. You can traverse using them, but you cannot modify the values they point to. This immutability is valuable in several scenarios. When working with functions that must not alter other container, when you want to guarantee safety in large collaborative code bases. In code, we use cbegin and cend instead of begin and end to get const iterators. This ensures your code won't compile if someone tries to modify an element within the loop. Const iterators enforce discipline. Sometimes we want to iterate in reverse order, from the end of a container to the beginning. STL offers a neat solution, reverse iterators. To use them, we call rbegin and rend on a container. For constant access, we use crbegin and crend. For instance, you can see this code. This prints the vector from the last element to the first. Reverse iterators come in handy in sorting, backtracking algorithms, or whenever the last elements have higher priority, like when implementing undo features or history stacks. It's time to look at an example that uses all 3 major iterator types: the regular, constant, and reverse. In this code snippet, the regular iterator iterates and updates the vector elements. The constant iterator ensures read-only access. The reverse iterator prints the modified values in reverse. By mixing and matching these iterator types based on your requirements, you gain both flexibility and safety in your code. Now it's time to take a step further into custom iterators. Why do we need them? Imagine you are creating a new data structure like a graph or matrix. To make it compatible with STL algorithms like for each or sort, your class needs to expose an iterator interface. Custom iterators provide that interface. They allow you to define how your object should be traversed. It's a powerful tool that elevates your C++ skills, especially if you ever work with non-STL data structures or build your own. Here's a simple example of a custom iterator embedded inside a class. We have a myContainer class with a nested iterator class. This iterator overloads key operators like not equal to, plus plus, and asterisk multiplied, allowing us to use it in a range-based for loop. We define begin and end to return instances of our custom iterator. This way our class becomes iterable, just like STL containers. This is a basic version, but it captures the core idea. In production, you would add bounds checking and possibly support for reverse iteration too. Let's go over a few common mistakes when working with iterators so you know what to avoid. Modifying with const iterator. You will get a compile error if you try changing elements. Use regular iterators when updates are required. Incorrect use of and in reverse iteration. If you use AND instead of RN in reverse loops, the logic breaks, referencing invalid iterators. This happens when you access an element after erasing it or from an empty container. Always validate your iterators. Avoiding these pitfalls will save you from undefined behavior and confusing paths. To reinforce your understanding, try out these problems. Reverse print a vector using both for loops and reverse iterators. Create a matrix wrapper class and implement a custom row-wise iterator. Use reverse iterators with a map to print key value pairs in descending key order. Compare regular versus constant iterator usage and performance. These exercises will help you apply today's concepts and build deeper familiarity with iterator mechanics. Here's a fun mini challenge. Write a function called print backwards that takes a dequeue of strings and prints each element in reverse using a reverse iterator. This exercise checks your understanding of both containers and reverse traversal. Try implementing it after this lesson. It's a short but insightful. Let's wrap up. Today we have learned what iterators are and how they abstract traversal in STL, how to use constant iterators for safety and reverse iterators for backward traversal, the 5 categories of iterators based on their power, and how to write a basic custom iterator to make your classes STL compatible. You also reviewed pitfalls and practiced real problems. With iterators in your toolkit, you are now ready to work more efficiently with STL containers and algorithms. Great job today! Welcome everyone to day 21 of our STL journey. This marks a major milestone. You have completed 3 full weeks covering containers, iterators, and associative structures in depth. Today's session is a special one. It's focused on applying everything you have learned so far. We will begin with a rigorous practice set that targets real-world STL usage. Then we will dive into a comprehensive mid-course quiz to evaluate your understanding and highlight areas for improvement. Let's dig in. Here's our roadmap for the day. First, we will spend around 3.5 hours working through STL-based practice problems. These problems are carefully designed to span across the different containers and concepts we have covered. Then comes the 90-minute mid-course quiz. This will assess both your conceptual clarity and your ability to write STL-rich code. After that, we will go into a review and feedback session, where we will discuss the trickier problems, explore different solution approaches, and reflect on your performance. Finally, we will look forward to week 4, where we begin exploring the incredible power of STL algorithms. Let's get clear on the objectives for our practice session. First, we want you to strengthen your foundation in using STL containers. You have seen how to declare and manipulate vectors, dequeues, maps, and more. Now it's time to apply that knowledge. Second, we want to help you build confidence through problems that mimic real programming scenarios, whether it's system design or competitive coding. Lastly, today's problems will challenge you to apply custom iterators and comparators, concepts that are essential when moving beyond textbook use and into real-world STL usage. By the end, you will not just understand STL, you will be using it like a pro. Let's quickly revisit the STL containers that are in focus for today's practice problems. First, vectors. You will use vectors to manage dynamic data like student records or sorted lists. We will focus on operations like pushback, insert, erase, and resize, and we will play around with nested vectors and sorting pairs. Then comes a dequeue or doubly ended queue. You will use this in problems that require efficient insertion and deletion from both ends. Think of problems like sliding window maximum or browser history simulation. The list, a doubly linked list implementation, will be used in safe insert delete operations where maintaining iterators is critical. With stacks and queues, we will implement classic concepts like expression evaluation, valid parenthesis check, and job scheduling queues. This will build your LIFO and FIFO logic muscles. Moving to the second set of containers, these are slightly more advanced. The priority queue will be used for problems that require frequent access to the highest or lowest elements. You will implement top K frequency problems and work with custom or comparators to control ordering. With sets and multisets, we will look at how to remove duplicates, perform range queries, and track counts of repeated elements. Then we move to maps and multimaps. You will build frequency tables, groupings, and record trackers. This will be helpful in problems involving word counts, student marks, or inventory systems. Finally, we will experiment with iterators, especially rewards and constants. You will also write your own functors and comparators to sort elements based on custom logic. Altogether, these containers and concepts form the backbone of modern C++ problem solving. Let's walk through some of the practice problems you will be working on today. Problem 1 involves using a vector of pairs to store student names and marks, then sort them by marks in descending order. In problem 2, you will implement a sliding window maximum algorithm using a DQ. This is a classic real-world pattern seen in stock analysis or real-time monitoring systems. Problem 3 is a browser history simulator using a list, allowing you to go forward and backward while preserving your iterator positions. Problem 4 requires you to design a min stack. You will use two stacks to track the minimum element at every stage. In problem 5, you will combine maps and priority queues to find the top 3 most frequent elements in a list. And in problem 6, you will use a set with a custom comparator to store and sort employee records based on joining date or salary. These problems offer a powerful blend of logic, design, and STL fluency. Here's how the practice assignment is structured. You will receive a PDF problem set with detailed instructions. Each question comes with an input format, output specification, and examples to test your logic. You are encouraged to solve this using either a local C++ IDE like Visual Studio Code or on competitive platforms like HackerRank or LeetCode for a timed environment. Remember to focus on code readability, proper use of STL functions, and logarithmic efficiency. Finally, discuss your approaches with your peers. If you are working in a group or classroom, collaborating on edge cases and optimizations will help deepen your understanding. Now let's talk about the mid-course quiz. This is a 90-minute assessment worth 60 marks. It's designed to test everything from syntax and logic to real-world STL application. The quiz covers material from days 1 through 20, including vectors, stacks, sets, maps, iterators, and more. We are using a mixed format structure to give you a well-rounded challenge. Let's look at the breakdown next. Here's how the quiz is structured. First, you will face 10 multiple choice questions designed to test your conceptual clarity, things like time complexity, container properties, and STL functions. Next, there are 5 output prediction problems. You will be given small STL code snippets and asked to find the output. Then come 5 syntax filled questions and where you will complete a code segment by choosing the correct STL code. After that, you will solve 2 short coding questions where you will write STL heavy code for a small task. Finally, there are 2 scenario-based problems. You will be given a real-world use case and asked to choose the most optimal STL structure to implement it. This quiz is a true STL skill set. It pushes your syntax, logic, and design thinking. Here are a few sample quiz questions to give you a feel. MCQ, which STL container offers constant time insertion at both ends but not in the middle. Output prediction. What's the output of a vector after calling insert v.begin plus 2, 5 on a vector of size 4? Syntax fill. Fill in the blanks to erase all elements greater than 10 from a multiset. Coding task. Write a function that returns the top 3 frequent elements using a map and priority queue. Scenario. You are building a undo redo system. Which STL container would you choose and why? These questions are as close to real-world thinking as possible. Let's reflect on what you will walk away with today. You will have practical experience with STL through diverse problem solving. You will see firsthand how STL saves time, simplifies logic, and makes your code robust. You will also gain feedback on your performance, which STL concepts you have mastered, and which areas need further attention. More than that, you will experience the joy of solving real problems, problems that mimic challenges faced in product development, software interviews, and competitive contests. Today is about leveling up, not just in knowledge, but in confidence. That brings us to the end of today's session. We will now have a quick wrap up discussion, highlighting creative solutions, common mistakes, and how to optimize further. Then we will look at your quiz results, compare scores anonymously, and talk about strategies for improvement. And as we step into week 4, get excited. We will dive into the power of STL algorithms. Functions like sort, count if, partition, and accumulate are about to transform how you solve problems. You have done great so far. Let's keep the momentum going. Welcome to day 22 of our journey through the standard template library. Today marks a turning point as we transition from learning STL containers to harnessing their full potential using STL algorithms. We will begin by exploring three fundamental yet powerful algorithms: sort, find, and count. These are not just utilities, they are high performance, industry grade operations that replace repetitive manual logic with elegant, optimized one liners. By the end of this session, you will be able to use them confidently across real world scenarios. Let's begin by understanding what algorithm is. It's a C++ standard header file that provides over 60 functions that work on containers using iterators. Think of it as a toolbox filled with essential utilities: sorting data, finding elements, counting frequency, removing duplicates, transforming sequences, and much more. These algorithms don't belong to the containers themselves. Instead, they operate on them, using iterators as access points. This design enables high reusability and separation of concerns. You will use containers to store and algorithms to operate. Why should we use STL algorithms instead of writing loops ourselves? The answer lies in performance, readability, and abstraction. STL algorithms are extremely well optimized, often better than what we might hand code. They make code concise and expressive. Instead of writing a 5-line loop to sort or search, a single function call does that job. They also encourage consistency, reduce room for errors, and integrate beautifully with lambda functions and custom comparators. In short, they let you focus on what you want to do, not how to do it. Our first algorithm today is sort. It's one of the most commonly used algorithms in C++. The syntax is simple: std : sort, start, end. This sorts the elements in ascending order using a less than operator by default. If you want custom sorting, you can pass a comparator function or a lambda. Note that sort works only with random access iterators, so vectors, arrays, and deques are okay. But sets, maps, and lists won't work because their iterators don't support random access. Keep that in mind when choosing your containers. Let's bring sort to life with an example. Suppose we have a vector of integers 5, 3, 9, and 1. A call to std : sort v.begin, v.end will sort it in ascending order, giving us 1, 3, 5, and 9. If we want descending order, we can pass a comparator greater. This flips the sorting criteria to use greater than symbol. Notice how elegant and readable this is. No nested loops or manual swap. It's production grade sorting with just one line of code. Next up, find. Searching is a basic but critical operation, and std : find makes it effortless. The function takes a range defined by iterators and a value to look for. It returns an iterator pointing to the first occurrence of the value, or the end iterator if the value isn't found. It works with all containers that provide iterator access: vectors, lists, deques, strings, you name it. This is perfect for quick membership checks and location-based logic. Let's look at a practical example. Consider a vector of integers, say 1, 2, 3, and 4. We want to know if the number 3 exists in it. We call std : find v.begin, v.end, 3 and store the result. If the iterator is not equal to v.end, that means the value was found. You can even calculate its index by subtracting v.begin from the iterator. This is a very efficient and clear way to search through containers without writing error-prone loops. Third algorithm for today is count. It helps us find how many times a certain value appears in a container. Like the others, it takes a range and a target value. It returns an integer, the number of times that value occurs. This is incredibly useful in data analysis, frequency tracking, and validation logic. Whether you are counting votes, characters in a string, or repeated inputs, count is your friend. Here's a clear use case. Imagine a vector with the elements 1, 2, 2, 3, and 2. You want to know how many times 2 appears. std : count v.begin, v.end, 2 gives you the answer, which is 3. That's it. No loops, no counters, no conditionals. One line. That's the elegance STL algorithms bring to the table. Before we wrap up, let's talk about common mistakes. First, never forget to include algorithm, otherwise these functions won't compile. Next, avoid trying to sort containers like std : set or std : map. They are already sorted internally and don't support random access iterators. Also make sure the iterator range you provide is valid. For example, don't reverse begin and end. Finally, understand the difference between begin and cbegin, especially when working with const containers. It's time to get your hands dirty. Try these practice tasks. First, sort a vector of strings alphabetically. Second, count the number of times the character A appears in a string. Third, use find to locate an element in a DQ. And lastly, sort a vector of pairs based on the second element using a custom comparator. These tasks are great for solidifying your understanding and getting comfortable with syntax and iterators. Let's see how much you have absorbed. Quick quiz. What does std : find return if the value isn't found? Can sort be applied to sets? How do you sort a vector in descending order? And what's the time complexity of sort? These questions not only reinforce your learning but also prepare you for interviews and coding competitions. To summarize, today you have taken your first steps into the world of STL algorithms. You learned how sort helps you order elements efficiently, how find lets you search with clarity, and how count simplifies frequency tracking. These three are just the beginning. The STL algorithm suite is fast and powerful. In the coming days, we will build on this foundation and unlock even more powerful tools like binary search, partition, accumulate, and next permutation. See you in the next session. Welcome to day 23 of our STL course. Today we explore a very practical and high performance category within the standard template library, the searching algorithms. These algorithms powered by binary search logic help us perform incredibly fast lookups, range queries, and data analysis tasks in logarithmic time. We will be diving into 4 essential functions: binary search, lower bound, upper bound, and equal range. By the end of this session, you will not only understand how each of these works, but also how and when to use them to write efficient, clean, and elegant C++ code. Before we even begin using these algorithms, there's one non-negotiable condition. Your input must be sorted. All these functions are built on the assumption that the data is in ascending order. Why? Because they use a variation of binary search internally, and binary search only works correctly when the data is sorted. So whether you are using vectors or arrays, make sure the data is sorted before applying these algorithms. If not, the results will be unpredictable and incorrect, which can be a huge issue, especially in production or competitive programming environments. Let's start with the most straightforward one, binary search. The syntax looks like this: binary search start, end, value. This function checks if a value exists in the given range. It returns a boolean, true if the element is found, false otherwise. What makes it powerful is its simplicity. Just a single call and you instantly know whether a value exists in your dataset. Use it when you don't need the position of the element, just a yes or no check. Moving on to lower bound, this function is your go-to tool when you are looking for the first element that is greater than or equal to a target value. It returns an iterator or simply the index, pointing to where this condition is first met. The syntax is auto it equals to lower bound, auto it assigned lower bound start comma end comma value. This is super useful when you are trying to find insertion points or calculate how many values are less than a certain number. For example, in a sorted array, lower bound helps in determining the starting position of a number, even when there are multiple duplicates. Now let's talk about upper bound. This one is closely related to lower bound, but with a subtle and important difference. Upper bound gives you an iterator to the first element that is strictly greater than the target value. The syntax is auto assign upper bound start comma end comma value. So if you have multiple instances of a value, say several 4s, upper bound will give you the position right after the last 4. It's especially useful when used in combination with lower bound to calculate frequency or define ranges. Now here's a neat utility, equal range. This function is a convenient wrapper that returns both the lower and upper bounds in one call. The syntax for this is auto range assign equal range start comma end comma value. It returns a pair of iterators. The first one points to the first element not less than the value, same as lower bound. The second one points to the first element greater than the value, same as upper bound. This is especially handy when you are working with sorted data containing duplicates. It allows you to quickly get the range of equal elements, for example finding how many 4s exist in a sorted vector. Let's visualize this concept with a real example. Suppose you have the sorted array 1, 2, 4, 4, 4, 5 and 6. Lower bound 4 will return the index of 4, which is 2. Upper bound 4 returns index 5, the first number greater than 4. So the equal range 4 gives us a subrange from 2 to 5 that includes all the 4s, and binary search 4 will return true because 4 exists in the array. Understanding how these positions map in a sorted container helps us design range-based queries and frequency calculations with high performance. Here's a simple C++ example that uses all 4 functions. This code snippet demonstrates the power of STL's searching suite. You can quickly check for presence, get positions, and find subranges all in logarithmic time. So where exactly do these searching functions shine? In counting frequency, like how many times a number appears in a sorted array. In range queries, such as how many elements are less than or equal to a value. In competitive programming, where time efficiency is critical, or when you want to use sorted vectors as a lighter alternative to sets and maps for cache-friendly performance. The best part is all these functions run in log n time, so even with large data sets, you will see consistent, blazing fast performance. To truly master these functions, try solving problems like count the number of times a particular value appears in a sorted array, find how many elements are less than or equal to a given value, count the number of elements between two values a and b, implement a binary search with a custom comparator such as for descending order or structs. These exercises will give you confidence and solidify your understanding of how these algorithms behave under various scenarios. Let's wrap up with a quick recap. These STL search functions are extremely powerful, but they only work correctly on sorted data. Binary search checks for existence. Lower bound finds the first position not less than the value. Upper bound finds the first position greater than the value. Equal range gives us the complete range for a value in one go. These tools let us write less code and get more drawn efficiently and elegantly. Make sure to practice them well. They are not just useful, they are very much essential. Welcome to day 24 of our journey through the standard template library. Today we are focusing on a class of algorithms that help us modify data in place. Powerful tools like copy, replace and remove, as well as their smarter counterparts, copy if, replace if and remove if. These aren't just utilities, they form the backbone of clean, efficient C++ code that works across containers with minimal boilerplate. Whether you are processing a dataset, transforming input, or filtering out unwanted entries, modifying algorithms can drastically simplify your workflow. Let's start by understanding what modifying algorithms are. In the STL, these algorithms operate not on containers directly, but on iterator ranges. That distinction is critical. They modify the elements within a range, like a segment of a vector or list, but they don't add or remove elements on their own. That means they won't change the container size, which is especially important to remember when you are using algorithms like remove. They work with various iterator types such as input, output, and forward iterators depending on the specific algorithm. In essence, modifying algorithms enable a functional, declarative approach to working with your data. You describe what you want to do, and STL takes care of the rest. std::copy is a basic yet powerful tool that lets you duplicate a range of elements from one container to another. It's commonly used when you want to replicate a dataset or apply filtering before operating on it. But sometimes you don't want to copy everything, just the items that classify a condition. That's where std::copy if comes in. Let's look at the code. We have a vector of integers from 1 to 5. First we copy all of them into another vector. Then using copy if, we only select the even numbers. The condition is specified using a lambda. In this case, x modulo 2 equals to 0. Note, if the target container does not have enough space allocated, you must use back inserter to safely append elements. Next up, we have replace and replace if. These algorithms are perfect for bulk transformations, changing every occurrence of a specific value or every value that meets a condition. For instance, suppose we want to replace every 2 in a vector with 10. Replace does this efficiently. But what if the rule is based on a condition, like replacing all values greater than 4 with 0? Then we turn to replace if, passing a predicate function that defines which values qualify. Again, these changes are made directly to the existing container, so be mindful if you are working with constant iterators or need to preserve the original data. Now let's tackle remove and remove if. These algorithms are slightly more nuanced. At first glance, they seem to delete elements from a container, but they don't. Instead, they rearrange the elements in place, pushing unwanted values to the end and returning an iterator to the new logical end. To truly erase these elements, we have to call .erase on the container using that returned iterator. For example, if we want to remove all 2's from a vector, remove helps reposition the remaining elements, then erase trims off the trail. The same applies to remove if, which uses a predicate. In this slide, we are removing all odd numbers from a vector. Again, first repositioning them with remove if, then erasing. This brings us to a fundamental STL pattern, the erase-remove idiom. It's vital to remember that remove and remove if only shifts values. They don't actually reduce the container's size. The leftover elements at the end remain unless explicitly removed. So the full idiom is container.erase remove, container.end. This works beautifully with vector and dequeue, where random access and erase operations are cheap. You will find this pattern in most high-quality C++ code bases. It's a sign of STL fluency. Let's apply this to a real-world example. Suppose you are preprocessing some input data that may contain invalid or unwanted values. Here we are working with a vector of integers. We want to remove all negative numbers and convert any zeros to ones. Using remove if, we eliminate the negatives. Then with replace we transform the zeros. In just a few lines, the data is clean and ready for further processing. This is the power of STL modifying algorithms: expressive, composable, and efficient. Before we go wild with modifying algorithms, here are some best practices to follow. First, never forget the .erase step after using remove. Without it, your container will contain garbage at the end. Second, if your destination container does not already have enough space, use std::back inserter with copy or copy if. Otherwise, you will run into undefined behavior. Third, avoid overlapping ranges when using these algorithms. For instance, copying from a container into itself without caution can lead to subtle bugs. Lastly, chain your algorithms when possible. This leads to clean, declarative, and readable code. Let's quickly recap what we have covered today. Use copy and copy if when you want to duplicate or filter data into a new container. Use replace and replace if to transform values in place based either on equality or a condition. Use remove and remove if to filter out unwanted elements. But remember, you must follow it up with erase to truly remove them. All of this work on iterator ranges, not containers. So understanding iterator mechanics is key. Now it's your turn to get hands-on. Here are some practice problems to help you internalize today's concepts. Write a function that copies only prime numbers from one vector into another. Use replace if to convert all negative values in a list to their absolute values. Remove all elements divisible by 3 from a TQ using the erase remove idiom. And for a bonus, filter a list of strings to remove those with fewer than 5 characters. These exercises will cement your understanding of modifying algorithms and build your confidence in applying them in real code bases. Hello and welcome back to day 25 of our journey through the standard template library. Today we are diving into an exciting and practical category of STL algorithms, partitioning and rearranging. These are not just abstract ideas, they power real-world features like filtering data, rotating buffers, and generating permutations. Let's explore how these algorithms help us manipulate sequences in powerful and elegant ways. Partitioning and rearranging algorithms form the core of many transformations in data structures and algorithms. Whether you are building a game engine, working on a calendar application, or preparing for a coding contest, the ability to reorder and filter elements efficiently is essential. In this session, we will focus on 3 categories: partitioning, rotating, and permutations. Each of these unlocks a different dimension of STL's capacity. Let's start with the partition algorithm. It takes a range and a predicate and splits the elements into 2 groups, those that satisfy the predicate and those that don't. The key thing to remember is that this split happens in place and is not stable. This means while the elements are correctly grouped, their original relative order is not preserved. This gives us excellent performance. It's very efficient, but you lose ordering. Here's a simple code example. We have a vector of integers and we want to bring all the event numbers to the front. We call partition with the begin and end iterators and a lambda function that checks if an element is divisible by 2. After the operation, all even numbers are grouped at the front, but not necessarily in their original order. The returned iterator points to the first element that does not satisfy the predicate, which is useful if you want to work with just the true or false halves. Now what if you do care about preserving the order? For that, STL gives us stable partition. It works similarly. It still separates elements based on a condition, but it preserves their original ordering within each group. This stability is crucial when the sequence has a meaning. For example, if you are separating students who passed and failed an exam and still want them listed in roll number order, it's slightly more memory and time intensive than partition, but the clarity it brings to structured data is often worth it. Let's look at a side-by-side comparison. On the left, partition, it's fast, requires no extra space, but it does not maintain the original order. On the right, stable partition, slower and may use extra memory, but it guarantees that the relative positions of elements are preserved. As a thumb rule, if order matters, go for stable partition. If performance is critical and you don't care about order, partition is your go-to. Next, let's talk about rotate. This algorithm rearranges elements in a circular manner. Imagine an array being cut at a middle point and then glued back such that the middle becomes the beginning. In terms of symmetry, you provide 3 iterators: begin, middle, and end. The elements in the range middle, end are moved to the front and the elements in begin, middle are pushed to the back. It's great for cyclic data structures such as round robin scheduling or rotating logs. In this example, we have a vector 10, 20, 30, 40, and 50. We use rotate with the middle at begin plus 2, which points to 30. The vector is rotated so that 30 becomes the new first element, resulting in 30, 40, 50, 10, and 20. Notice how the rotation wraps around like it's a circular shift. This behavior is often used in problems where you need to maintain a moving window or adjust the order using without inserting or deleting. So where might you use rotate in real life? A few ideas: in a music player that cycles through songs, in a scheduler that rotates through available tasks, or in a graphical interface that scrolls elements in a carousel. It's also useful in algorithms like quicksort and for simulating left or right shifts in arrays, which show up in many coding problems. Now for one of the coolest STL algorithms, next permutation. This function rearranges the elements into the next lexicographical permutation. If you keep calling it repeatedly, you will cycle through all the permutations of a container. There's also pref permutation, which works in the reverse order. These are extremely useful in generating all arrangements of a set, for example, solving traveling salesman problems, puzzles, or combinations in interviews. Let's see it in action. In this snippet, we begin with the vector 1, 2, 3. We use a do-while loop to print every permutation until next permutation returns false, which happens when we reach the last permutation. Here's an important tip. Always sort your container before you begin generating permutations to ensure you start from the lowest lexicographical order. Otherwise, you may miss some permutations or get incorrect results. As powerful as these algorithms are, there are some common mistakes to avoid. First, don't assume that partition reverses order. Use stable partition if needed. Second, with rotate, the middle point you choose must be valid. Off by one errors are common here. And with the next permutation, always remember to sort your data first, or you won't start at the correct beginning. Let's tie this to real-world use cases. Imagine building a student result system. You can use partition to separate those who passed and failed. For a circular buffer of logs, rotate keeps your data fresh and within size limits. And for brute force approaches to puzzle solving or cryptographic pattern checking, next permutation lets you explore every possible order. Now it's your turn to apply what you have learned. Exercise 1. Partition a vector of integers into evens and odds. In exercise 2, rotate a vector to the left by 3 positions. In exercise 3, generate all permutations of a 4-element list. This will help you gain confidence with these algorithms and understand why they shine. To summarize, partition and stable partition help you split data conditionally. Rotate gives you fine-grained control over rearranging sequences. And the next permutation opens the door to exhaustive permutation logic. These algorithms are incredibly versatile and form a vital part of any STL programmer's toolkit. Here's your assignment for day 25. First, implement a circular buffer that uses rotate to simulate log action. Second, use partition to divide a list of students into pass and fail categories and then sort each group. Third, write a function to generate the kth permutation of a list. This will test your understanding of permutations and combinatorics. Happy coding! Welcome to day 26 of our STL course. Today we dive into the powerful numeric algorithms in the standard template library. We will focus on the 3 key functions from the numeric header: accumulate, iota, and inner product. These tools help us simplify operations like summing, generating sequences, and computing dot products. Let's explore how these algorithms can make your C++ code more elegant and efficient. The numeric header in the STL provides algorithms that are specifically geared towards numeric and arithmetic operations. Unlike generic log algorithms found in algorithm, this header offers targeted tools like accumulate for summing, iota for populating containers, and inner product for performing dot products or combining elements. These algorithms work seamlessly with iterable containers like vector and array, and they form the backbone of many real-world numerical applications. Accumulate is one of the most straightforward and widely used functions in numeric. It allows you to compute the total sum of a range with minimal code. Syntax is simple. You provide a range using iterators and an initial value. For instance, summing the contents of a vector can be done in a single line. This eliminates the need for verbose loops and helps you write concise and expressive code. But accumulate isn't limited to just addition, but supplying a custom binary operation like asterisk colon multiplies. You can perform other operations such as computing the product of all elements in a container. You can even define your own lambdas for more advanced behavior. This flexibility means accumulate can serve many roles beyond simple summation, like building strings, reducing conditions, or applying custom calculations. IOTA is a lesser known but extremely useful STL function that fills a range with incrementing values. It's often used to generate sequences like IDs, indices, or even arithmetic progressions. You specify the range and the starting value, and IOTA does the rest. It's efficient, clean, and saves you from writing manual loops to populate containers. Inner product computes the dot product of two ranges. It takes two input ranges and an initial value and combines the corresponding elements by multiplying and summing them. This is especially useful in vector matrix multiplication and signal processing. The power of this function lies in its ability to express what would otherwise be a multi-line loop in just one line. What's fascinating about inner product is that it supports custom operations. You can override the default addition and multiplication behavior with your own logic. This means you can use it for string manipulation, logical operations, or any complex pairwise transformation. For example, you could combine two strings character by character or even apply conditional logic on pairs of elements. This makes inner product a hidden gem for concise and powerful computations. Now it's your turn to practice. Try using accumulate to compute the sum and product of a list or count how many numbers meet a specific condition. Use iota to fill a vector with increasing numbers or generate multiples of a given number. Then use inner product to calculate a dot product or get creative and use it to combine strings or objects in a meaningful way. These exercises will help reinforce today's concepts through hands-on applications. To wrap up, we have seen how accumulate simplifies summing and reductions, how iota fills containers with sequences, and how inner product lets us pairwise compare elements with great flexibility. These numeric algorithms are invaluable when dealing with collections of data that need transformation or aggregation. As you continue your STL journey, keep these tools in your arsenal. They can greatly reduce code complexity and enhance performance. Finally, a word of caution. While these algorithms are powerful, there are times you might want to avoid them. For massive datasets, consider parallel algorithms or multi-threaded approaches. In real-time systems, avoid anything that could block execution or reduce predictability. And for complex logic, sometimes using loops may improve readability and maintainability. Like any tool, use this wisely and with context. Welcome to day 27 of our STL Mastery course. Today we are diving into one of the most elegant and powerful features of modern C++, the lambda functions. We will learn what lambdas are, why they are crucial in STL algorithms, how to write and customize them using capture lists, and see them in action through several practical examples. By the end, we will be writing expressive, clean code that integrates lambdas with standard algorithms like a pro. So what exactly is a lambda function? In C++, a lambda is simply an anonymous function, meaning a function with no name. It's defined inline, right where you need it, often in a single line of code. Lambdas were introduced in C++ 11 and have since become indispensable in functional style programming with STL. They are especially useful when working with algorithms that need small pieces of logic passed as parameters. Let's take a closer look at the syntax of a lambda function. A lambda is structured as capture list followed by parameter list, then optionally the return type, and finally the function body. The capture list allows the lambda to access external variables. Parameters define what inputs the lambda accepts. Most of the time you can omit the return type as it can be inferred. It's concise and incredibly flexible. Here's a simple yet powerful use case: sorting a vector in descending order. Using the sort algorithm with lambda, we pass a custom comparator right to the call. Notice how the lambda takes two integers, compares them using greater than, and the vector gets sorted in descending order, all without creating a separate function. This is clean, compact, and highly readable. The capture list is what gives lambda access to variables from the surrounding scope. Empty brackets mean you capture nothing. Square bracket equals captures everything by value, and while square bracket ampersand captures everything by reference. You can also be specific and capture individual variables either by value or reference. This mechanism provides precise control over what data your lambda uses and how. Lambdas shine brightest when combined with STL algorithms. Functions like sort, countif, foundif, findif, and removeif all accept a function object, and lambdas make it easy to provide that on the spot. Need a custom condition or operation? Just write a lambda right inside the algorithm call. It keeps your code concise, localized, and expressive. Let's count the even numbers in a vector. The countif algorithm takes a range and a condition. We pass a lambda that returns true when a number is divisible by 2. This one-liner replaces what would normally be a for loop and an if condition. It's efficient and readable, a hallmark of good modern C++. By default, variables captured by value are immutable inside lambdas. You can read them but not modify them. However, with the mutable keyword, you can change these values inside the lambda. Here's an example where a counter is captured by value but still incremented using mutable. But be careful with mutable captures. They modify the copy inside the lambda, not the original variable. Lambdas are just function objects, so you can store them in variable and use them like any other function. This is especially useful when you want to reuse the same logic multiple times. For example, here we assign a greater than comparator lambda to a variable and then use it with sort. It makes your code even cleaner and avoids duplication. Let's apply lambdas in a slightly more advanced example. Sorting a vector of structs. Suppose you have a list of students with names and marks. Using a lambda, you can sort them based on their marks or any other membered variable. This shows the true power of lambdas when combined with user-defined types and STL. Now it's your turn to get hands-on. Try sorting a vector of strings by their lengths using a lambda. Then use countif to count how many elements in a vector are greater than 50. Finally, remove all even numbers from a vector using removeif with a lambda. These exercises will help reinforce everything you have learned today. To summarize, lambda functions are compact, anonymous functions you can define inline. They work beautifully with STL algorithms and let you write expressive logic right where it's needed. With capture lists, parameter lists, and mutable support, you can handle a wide variety of cases, all with clean, modern syntax. Lambdas are not just a syntax sugar, they are an essential part of modern C++. Here's your assignment for today. First, sort a vector of pairs based on the second element using a lambda. Next, partition a vector into events and odds, again using a lambda to define the condition. Finally, capture a threshold value and use it in a lambda to filter out elements below it. This task will really cement your understanding of lambda functions in real case. Welcome to day 28 of our STL masterclass. Today we are taking everything we have learned so far, especially maps, strings, and algorithms, and applying them in a real-world mini project. We will build a text frequency analyzer, a compact yet practical application of STL to solve a very common problem in text analytics, understanding how frequently words appear in a piece of text. Let's explore how STL empowers us to solve this cleanly and efficiently. The goal of this mini project is to build a program that analyzes a block of text and counts the frequency of each word. Then it should display those frequencies sorted in descending order so we can quickly see which words appear the most. To keep it robust, we will also handle things like punctuation and case sensitivity, ensuring hello and hello are treated the same, and punctuation marks don't break words apart. This is a great example of how STL makes such tasks seamless. For this project, we will bring together several STL components. First, we will use either unordered map or map to store word frequencies. Then, iString stream will help us parse the input text into individual words. For cleaning the text, like removing punctuation and converting to lowercase, we will transform and remove if. Finally, we will use a vector of pair string comma int to sort the results and display them. These STL tools combined allows us to build this project with very little boilerplate. Text processing is an essential step in any text-based program. First, we remove punctuation marks using remove if in combination with is_punc. This ensures that symbols like commas, periods, and quotation marks don't interface with word separation. Then we use transform to convert all characters to lowercase, making our comparison case insensitive. Without these steps, we would end up with misleading duplicates like word and word being counted separately. Now that our input text is clean, we are ready to count the words. We use an unordered map where the key is the word and the value is the frequency count. We feed each word into the map using a while loop with an input string stream. If a word is seen for the first time, it's added to the map. If it already exists, its frequency count is incremented. This simple logic powered by STL turns our code into an efficient word frequency engine. Once we have tailed all the word frequencies, we need to sort them to find the most common words. Since unordered map and map do not allow sorting by value directly, we copy the map's content into a vector of pairs. Then we use sort with a custom lambda function to sort the pairs in descending order by frequency. This way the most important words appear at the top of the list, ideal for both display and analysis. With the sorted list in hand, we may also want to compute the total number of words processed. This helps us calculate word percentages or just get a sense of the text size. Using accumulate, we sum all the values, the frequencies from our vector of word pairs. The lambda inside accumulate simply adds each frequency to a running total. This one-liner STL trick is clean, fast, and very readable. We have now built a working word frequency analyzer, but there's a lot more you can do to level it up. For example, you can read the input from an external .txt file using if string. You could also filter out common stop words like da or is to focus only on meaningful words. Displaying the top 10 most frequent words or visualizing frequencies using ASCII bars is another great improvement. Finally, try switching between map and unordered map to compare performance in large inputs. This is a sandbox for experimentation. Here's a simple sample output from our analyzer. As you can see, the words are listed alongside how many times they appear in the text. This output can easily be formatted further or extended with bar charts, percentages, or color-coded highlights. Once you have understand the data structure behind it, enhancing it becomes a creative endeavor. To complete today's session, your assignment is to extend this project. Start by reading input from a .txt file and skipping commonly used stop words. Then try to display only the top 10 most frequent words and include the percentage each contributes to the total. For those feeling adventurous, implement a menu-driven console interface that allows users to select options interactively. This assignment is your opportunity to integrate STL with real-world design patterns. Welcome to day 29 of our STL course. Today we are going to explore two advanced but essential concepts in the standard template library: function objects and predicates. These powerful tools will allow you to have finer control over STL algorithms, making your code more efficient and flexible. By the end of this session, you will learn how to define custom function objects, also known as functors, how to use predicates for algorithm customization, and the benefits they bring to your programming toolkit. Here are the objectives we will cover in today's session. We will start by defining function objects and exploring their syntax. Next, we will delve into the powerful built-in function objects that come with a functional header in C++. After that, we will focus on creating custom functors both with and without state so you can define your own logic in algorithms. We will also explain how function objects differ from function pointers and lambdas and when it's best to use each of them. Lastly, we will explore how predicates are used in STL algorithms to filter, compare, and transform data. Let's begin by understanding what a function object is. A function object or functor is simply an object of a class or struct that overloads the operator. This gives the object the ability to behave like a function, making it callable with a bracket syntax. Unlike regular functions, function objects can store state and contain multiple methods. This compatibility gives them a distinct advantage, especially when you need to encapsulate behavior with internal state. For example, the square struct you see on this slide overloads operator to compute the square of an integer, which means it can be used as a callable function in your program. So why would you use function objects in your C++ code? The primary reasons are flexibility, reusability, and performance. Functors can store state. This means they can keep track of data across multiple calls, unlike regular functions. For example, you can create a functor that counts how many elements satisfy a certain condition. Functors are reusable, which means once you define them, you can use them across various algorithms. Another important point is that functors are more optimized by the compiler, especially when used in STL algorithms, leading to better performance. Overall, functors are more object-oriented way to introduce function-like behavior into your code. The C++ standard library provides a variety of built-in function objects in the functional header, and these can be used in your algorithms immediately. Examples include plus, minus, greater, less, and more. These are template-based, meaning you can use them with any data type. For instance, if you want to sort a collection of descending order, instead of writing your own comparison function, you can simply use greater int. These built-in function objects are convenient and they reduce the need to write custom functors for common operations. This gives you more readable and concise code. While built-in function objects are useful, there are times when you need more control over the logic. This is where custom functors come in. A custom functor allows you to define your own behavior for specific tasks. For instance, here we have created a functor called isEven, which checks if a number is even by overloading operator. The logic is simple. It returns true if the number is divisible by 2 and false otherwise. You can then pass this functor into STL algorithms like countif, which counts how many elements in a container satisfy the condition defined by your functor. Custom functors give you the power to tailor algorithms to your specific needs. One of the powerful features of functors is that they can hold state. Unlike regular functions or lambdas that cannot store any data outside of their execution, functors can maintain internal data across multiple invocations. For example, in the counter functor, we track how many times the functor has been called by maintaining a count variable. When applied in an algorithm such as countif, it increments the count each time it is invoked. Stateful functors are especially useful when you need to maintain contextual information during algorithm execution or apply complex logic repeatedly across elements. Now let's talk about predicates. A predicate is simply a callable object, whether a function, lambda, or functor, that returns a Boolean value. Predicates are commonly used in STL algorithms where they help determine whether certain conditions are met. There are two types of predicates, unary and binary. A unary predicate takes a single argument and returns a Boolean, while a binary predicate takes two arguments and returns a Boolean. Predicates are central to STL algorithms like countif, findif, and removeif, where they define the condition or logic for comparison and filtering. Here's a practical example of a predicate in action. We use a lambda expression with removeif to filter out all negative numbers from a vector. The lambda acts as a unary predicate, returning true if a number is negative and false otherwise. Remove if will then remove all the elements that satisfy this condition. This is a great example of how predicates give you the flexibility to easily customize STL algorithms with just a simple callable. Whether using function objects, lambdas, or function pointers, predicates make algorithms dynamic and adaptable. It's important to distinguish between functors, function pointers, and lambdas. Each of these has unique features and advantages. Functors, as we have discussed, are objects that can store state and offer reusable logic. Function pointers are more lightweight and concise, but they cannot capture state or store data. Lambdas, on the other hand, are anonymous functions that can capture variables from the surrounding scope. The key difference between functors and lambdas is that functors are more reusable since they are full-fledged classes. Function pointers are typically used when you need to pass around simple function references. Knowing the differences helps us decide which to use in various situations. Now let's look at the real-world use case of functors and predicates. Functors and predicates are widely used in STL algorithms like sort, find if, count if, remove if, and transform. For example, you can use a custom comparator in sort to order functions to order elements in a specific way, or use count if with a predicate to count how many numbers in a vector are greater than a particular value. By leveraging the power of function objects and predicates, you can write more expressive, efficient code. Functors and predicates are incredibly versatile tools that let us embed complex logic directly into our algorithms. It's time for some hands-on practice. First, try writing a functor called isPrime that checks if a number is prime. Next, create a functor named rangeChecker that accepts a minimum and maximum value and checks if a number falls within that range. Finally, use a custom functor to sort a collection and count how many comparisons it performs. These activities will help you solidify your understanding of functors and predicates and how they can be used to optimize your code. To summarize, function objects or functors are classes that overload the operator and behave like functions. They can hold state and be reused across various algorithms, offering more flexibility than traditional functions. STL provides many built-in function objects in the functional header for common tasks. Predicates are just callable objects that return a Boolean value and are heavily used in filtering and searching algorithms. Understanding how and when to use functors and predicates will make you a more effective C++ programmer, allowing you to harness the full power of the STL. Before we finish, let's do a quick review. First, what is a functor and how does it differ from a regular function? Second, which STL header provides the built-in function objects like plus, minus, and greater? And third, can you write a functor that checks if a number is divisible by 3? Take a moment to answer these questions and reinforce what you have learned today. Welcome to day 30 of our STL template library course. Today we will explore 4 powerful and incredibly useful utilities in C++: pair, tuple, array, and bit set. These containers are essential for simplifying complex data structures and improving both the readability and efficiency of our code. Whether we are grouping values, working with fixed size arrays, or manipulating bits, these STL utilities will help us write more expressive, efficient, and maintainable code. Why should we use these STL utilities in our code? Well, STL containers help simplify the complexity of our programs. They reduce competitive grouping, repetitive coding, enhance readability, and provide clear, high-level abstractions for tasks like grouping values or manipulating data at the bit level. By leveraging pair, tuple, array, and bit set, you make your code easier to understand, maintain, and optimize. These utilities are not only vital for real-world applications but also widely used in competitive programming, where space and time efficiency are critical. Let's start with pair. A pair is a simple yet incredibly useful container that can hold two values of possibly different types. It is defined in the utility header, and its primary use is to store two related pieces of data. For example, you might use a pair to represent a coordinate, a key value pair in a map, or even return two values from a function. You can easily access the two values pair in a pair using dot first and dot second. This makes it a great tool for quick, compact data storage. Moving on to more advanced pair usage. While pairs are commonly initialized directly, you can also use make pair for more clarity and automatic type detection. This is particularly useful when the types of the elements are not explicitly obvious. Pair also supports comparison operators, allowing us to easily compare pairs based on their first and second elements. You can even nest pairs to create more complex structures such as multi-dimensional keys for sorting or searching. Let's consider an example where we compare two pairs and check if one is greater than the other. Next, let's dive into tuple. Unlike pair, which can only hold two values, a tuple can hold any number of values, potentially of different types. This makes it perfect for situations where you need to group multiple values together. For example, you might want to return a student's ID, name, and grade from a function. The beauty of tuples is that they allow you to store heterogeneous data in a single object. You can access the tuple elements using std::get, or if you are using C++17 or later, you can use structured bindings for a more intuitive and readable approach. Tuples come with some incredibly useful utilities. For example, std::type allows us to unpack a tuple into individual variables, which can be very handy when dealing with function returns or complex data structures. If you don't care about certain values in a tuple, you can use std::ignore to skip them. Additionally, std::tuple-cat lets us concatenate multiple tuples into one, which is useful for combining different sets of data into a single entity. Now let's talk about std::array, which is a safer and more powerful alternative to traditional C-style arrays. Defined in the array header, std::array has a fixed size that is known at compile time. This gives us the safety of bounds checking when accessing elements, and it integrates smoothly with STL algorithms like std::sort, std::file, and std::for each. Unlike a regular array, you can directly use these algorithms with std::array, which makes it a much more modern and reliable choice for fixed size collections. With std::array, you gain access to several useful methods. For example, .size gives you the number of elements in the array, and .add provides bounds check access to elements. The .front and .break methods allow you to access the first and last elements respectively. You can also use .fill to set all elements of the array to a specific value. For instance, you could fill an array with zeros using .fill0 and access any element using .add2, all while avoiding common array related pitfalls such as out of bounds access. Finally, let's take a look at std::bitset. Defined in the bitset header, std::bitset is a fixed size sequence of bits. It is perfect for situations where you need to perform binary operations such as bit masking, cryptography, or low-level data processing. With std::bitset, you can represent binary data cleanly and efficiently. For example, you can create a bitset to store a binary value like 10101100 and then use the .count method to count the number of bits that are set to 1. This makes it an ideal container for handling bit level manipulation. std::bitset comes with a variety of methods for manipulating bits. For example, .set lets us set specific bits to 1, while .reset sets bits to 0. Flip inverts the current state of the bits, and .tests checks whether a bit at a specific position is set. Additionally, .count counts how many bits are set to 1, and methods like .toString help us to convert a bit set back into a string for easy display or debugging. These methods make bitset incredibly versatile for bit level tasks. Let's summarize the key differences between these containers in a comparison table. Pair is ideal for storing two related values such as key value pair or a coordinate. Tuple, on the other hand, is perfect for grouping multiple heterogeneous values together. Array is a safer, more efficient alternative to traditional arrays, while bitset is specialized for efficient bit-level operations. Understanding when to use each of these containers is crucial for writing efficient and maintainable C++ code. To solidify today's lessons, here are a few practice problems. Try using pair to represent the coordinates or graph edges. Use tuple to return multiple values from a function or to represent complex data. Replace old C-style arrays with std::: array to take advantage of its safety features, and finally explore solving problems with std:: bit set, such as checking subsets or performing bit manipulation. To wrap up day 30, we have covered a variety of STL utilities that will make your coding more efficient and readable. std:: pair and std:: tuple allow us to group related values, while std:: array provides a modern, safer alternative to traditional arrays. std:: bit set offers powerful bit manipulation capabilities. Mastering these containers will give us the tools to write clean, efficient code, whether we are working on real-world applications or preparing for competitive programming challenges. Welcome to day 31 of our STL journey. Today we are going to dive deep into three powerful C++ 17 features: optional, variant, and any. These features help us write safer, more readable code when we need to handle optional values, multiple possible types, or dynamic typing. By the end of today's session, you will understand when and how to use these types in your C++ code. Let's get started. In traditional C++ programming, we often resort to using magic values like -1 or null ptr to signal missing or invalid data. While this can work, it's error prone and not very expressive. Instead, modern C++ gives us with three tools: optional, variant, and any. These tools allow us to communicate our intentions clearly, making our code easier to read and maintain. They also help us avoid dangerous pitfalls like dereferencing null pointers or dealing with hard-to-crack magic numbers. Today we will explore how these wrappers make your life as a C++ developer much easier. Let's start with std:: optional. An optional is a type that might or might not contain a value. It's like a box that could either be filled with something or be empty. For example, imagine a database query where the result could be absent. Instead of using -1 or null ptr, you can return an optional int to indicate that a value may or may not be present. To check if the value exists, you can use .hasValue or just cast it to bool. To retrieve the value, you can use .value, but remember, you should first check if it exists. If it's empty and you call .value, it throws std:: bad optional access, so make sure to handle that properly. While optional is powerful, there are best practices and pitfalls to keep in mind. Always check before accessing the value. You can do this by using .hasValue or by using the save.value or method that gives us a default value if it's empty. Avoid using optional with references. This is a tricky scenario that can lead to undefined behavior. Don't forget, accessing .value on an empty optional can cause runtime errors, so be sure to use it with caution. Now let's move on to std:: variant. Think of a variant as a type-safe union. Unlike traditional unions, which allow you to store one type of data but require you to manually manage the type you are storing, variant ensures that you can only access the value in a way that's safe for its current type. For example, std:: variant int, float, string can store either an int, a float, or string. But the key difference is the type is known at compile time, so you don't need to worry about memory issues or undefined behavior that can occur with traditional unions. To access the value inside, you can use getT or more commonly use visit to apply a function or lambda to the stored value, no matter what its type is. With std::visit, we bring the visitor pattern into our C++ code. This function takes a lambda or a function and applies it to the type inside a variant. For instance, you could apply a lambda to process the stored int, float, or string depending on the type of the value currently held by the variant. This is extremely powerful because you can easily handle multiple types without manually checking each one, making your code cleaner, more maintainable, and easier to extend. Next up is std::any. Any allows us to store any copyable type. This is runtime polymorphism in C++. We don't need to know the type at compile time. For example, you can store an int, a std::string, or a user-defined type inside any object. However, unlike optional and variant, which are type safe at compile time, any requires runtime checking. You can retrieve the stored value using std::any cast, but if the type does not match, it throws a std::bad any cast exception. While any is flexible, it comes with a performance overhead and a loss of type safety, so use it when you really need that flexibility. Here's a quick comparison table to help you remember the differences. Optional, used for a single value that might be present. Variant, a type-safe union that can hold one of several types. Any, a flexible container that can hold any type, but with less safety. Choosing the right one depends on your specific use case. Use optional when a value may or may not exist. Use variant for type-safe multiple options, and use any when the type is completely unknown or variable. Let's look at some real-world examples. Optional. Imagine querying a database for a user's profile picture. If the user does not have one, we return an empty optional std::string. Variant. Say you are building a configuration system. Your config file might contain a variety of values, an int for screen resolution, a bool for dark mode, and a std::string for the theme. Use variant to handle these different types safely. Any in a plugin system where different modules may pass values of completely different types. Any is perfect because it allows you to store and manipulate these values without prior knowledge of their types. Now it's your turn to implement what you have learned. Here are your tasks for today. Implement a function that returns an optional int for a user's age. It may be missing, so handle it carefully. Use variant to manage a set of configuration values. One can be an int, another a bool, and another a std::string. Create a simple logger that accepts any type using std::any. These hands-on tasks will help you internalize the concepts and practice using these tools in real code. Let's summarize what we have covered today. Optional, a wrapper for values that might not exist. Great for things like function results or optional data. Variant, a type-safe union perfect for cases where you know the set of possible types. Any, a flexible container for completely dynamic types, useful for things like plugin systems. Remember, choose the right tool for your situation. Don't overuse any when you can safely use optional or variant. Let's wrap up with a quick quiz to test your understanding. What happens if you try to access the value of an empty optional? A. It returns the default value. B. It throws a bad optional access exception. And C. It causes a compilation error. The correct answer is B. Always check if the optional contains a value before accessing it. Welcome to day 32 of our STL course. Today we are diving into custom comparators and functors in C++. These powerful tools allow us to control how data is ordered and processed in STL containers. By customizing your comparators, you will be able to define exactly how sorting, searching, and even prioritization are performed, giving us full flexibility when working with STL containers like set, map, and priority queue. Let's unlock the power of custom logic in our programs. Let's go over the learning objectives for today's lesson. By the end of this session, you will be able to understand what custom comparators are and why they are essential for specialized data sorting and searching. Learn how to define custom comparator logic using lambda functions and functors. Apply these comparators in STL containers and algorithms to achieve custom ordering. Finally, we will cover best practices to avoid common pitfalls when using custom comparators in your code. Let's get started. A custom comparator is simply a function or object that defines how two elements in a container should be compared. By default, STL containers like set and map use the less than operator to compare elements. However, when you need a different comparison logic, whether it's sorting in descending order, comparing by a specific attribute of an object, or creating a custom priority, you can provide your own comparator. Custom comparators are essential for tailoring the behavior of STL containers and algorithms to our needs. So why would you want to use a custom comparator? Well, consider this. You might have a list of people and you want to sort them by age, not by name. Or perhaps you want to sort numerical values based on their last digit instead of their actual value. Without custom comparators, achieving these would be challenging. Custom comparators allow us to define our own sorting rules, which is especially useful when working with associative containers like set, map, and priority queue. We can also integrate them into searching algorithms to control how comparisons are made. There are three main ways to define custom comparators in C++. Function pointers, the traditional approach where you create a function to compare two elements. This is a simple and clear method. Lambda functions, a modern and concise method where we define a comparator in place. It's great for small one-off logic. Functors, a function object that overloads the operator so we can call it just like a function. Functors are reusable, maintainable, and ideal for more complex comparison logic that needs state or customization. Each approach has its own strengths. We will explore these in more detail today, so we will be able to choose the right one for our needs. Let's start with the function pointer approach. Here we define a simple function called test that compares two integers and returns true if the first one is greater. This function is then passed as a comparator to the sort algorithm to sort a vector in descending order. While function pointers are a tried and true method, they can be a bit verbose and less flexible compared to other two methods, but they are great for simple one-time uses. Now let's look at lambda functions. Lambdas are quick inline functions and they allow us to define custom comparison logic without needing a separate function. In this example, we use a lambda to sort the vector based on the last digit of each number. The lambda expression is concise and works perfectly when you need a small, localized piece of comparison logic. This is a great choice when you don't want to clutter your code base with additional function names or when the logic is short-lived. Next, we have functors, which are objects that overload the function call operator. In this example, we define a compare by age functor that compares two person objects by their age. We then use this functor in a set, ensuring the elements are ordered by age. Functors are particularly useful when the comparison logic is more complex or needs to be reused multiple times. Unlike lambdas, functors can also maintain state, making them more flexible for complex use cases. Here's a great example of a lambda comparator with a priority queue. In this case, we are sorting pairs of integers where we prioritize the second element of the pair. By passing a lambda to the priority queue, we can customize the heap's behavior. This allows us to create a custom main heap where the elements are ordered according to a non-trivial comparison logic. This technique is particularly useful for scheduling tasks where tasks are prioritized based on their urgency and deadline. Which STL containers rely on custom comparators, primarily the associative containers, set and multiset. These containers use comparators to determine the order of elements, map and multimap. The keys in these containers are sorted based on a comparator. Priority queue. This container manages elements in a heap, and custom comparators can change the heap's ordering. On top of containers, many STL algorithms also use comparators. For example, sort, binary search, lower bound, and equal range all rely on comparators when they are provided. Custom comparators enable fine-tuned control over these algorithms' behavior. While custom comparators are extremely useful, there are some common pitfalls to be aware of. Our comparator must enforce strict weak ordering. This means that if A is less than B is true, then B is less than A must always be false. If this isn't the case, the behavior of containers and algorithms can be unpredictable. Avoid capturing variables in lambdas when used as comparators in containers. This is because containers like set or map may store a copy of the comparator, which could lead to unexpected behavior. Const correctness is essential. Ensure that functors are marked as const if they don't modify state. This allows them to be used correctly in containers that require const correctness. To wrap things up, there are some best practices. Use lambdas when your comparison logic is simple, short-lived, and does not need to be reused. Use functors for more complex or reusable comparison logic. Functors can also hold state, making them ideal for maintaining additional data during comparisons. Always ensure that your comparator is const correct if it does not modify any state. This is especially important when using functors with STL containers. Test your comparators thoroughly. It's easy to overlook edge cases, so always ensure that your comparators work correctly in all scenarios. Let's put our new knowledge to the test with some practice tasks. Sort a vector of pairs by their second element in descending order. Create a books chart and sort a set of books by publication year, then by title. Implement a custom main heap using priority queue to manage tasks based on priority and deadline. Now for your mini lab assignment, build a leaderboard system. Use a set or map with a custom comparator to rank players. Rank them first by score and then alphabetically by name. Implement functionality to insert and remove players and retrieve the top 5 players in order. Make sure to rank the scores in descending order. Before we finish, let's do a quick recap. Can you write custom comparators using lambdas and functors? Do you understand when and why to use function pointers, lambdas, and functors? Can you apply custom comparators to STL containers like set, map, and priority queue? Are you aware of the common pitfalls and best practices for comparators? If you can confidently answer yes to these questions, you are ready to tackle more complex STL problems with custom comparators. Thanks for joining today's lesson. Now that you understand custom comparators and functors, you can take full control over how data is ordered and processed in STL. If you have any questions, feel free to reach out. I will see you in the next class. Welcome to day 33 of our STL course. Today we are going to explore one of the most powerful combinations in algorithmic problem solving, STL and backtracking. Backtracking is an elegant technique used to explore all possibilities for solving problems with constraints. We will see how STL containers like vectors, sets, and maps can help us simplify and optimize these solutions. By the end of this session, you will be ready to apply these techniques to problems like generating subsets, finding permutations, solving n-queens, and even Sudoku puzzles. Let's dive in. Before we dive into backtracking, let's quickly refresh our understanding of recursion. Recursion is a method where a function calls itself to break down a problem into smaller subproblems. Every recursive solution has two critical parts: the base case, which stops the recursion, and the recursive case, which keeps breaking down the problem. Understanding recursion is crucial for solving problems with backtracking because it allows us to explore different states and systematically undo our decisions when they lead to dead ends. Backtracking is a powerful technique for solving problems that involve searching through all possible configurations. Rather than blindly trying each option, backtracking helps us prune the search space by abandoning paths that are invalid or unpromising. It's like navigating a maze and only moving down paths that could potentially lead to the exit. If you hit a dead end, you backtrack and try another path. This allows us to focus on more promising options without wasting time on fruitless paths. Backtracking is perfect for constraint-based problems like n-queens or Sudoku. where you need to satisfy certain conditions at each step. Now let's look at how STL containers come into play with backtracking. STL provides a wide range of containers that help us manage the state of our solution as we explore different paths. For example, vectors are great for dynamically building and removing elements as we generate subsets or permutations. Sets help us track states that we have already visited, ensuring that we don't waste time revisiting the same configuration. Maps, on the other hand, are helpful for memorization, where we store previously computed results to avoid redundant work, and we can even use stacks to simulate the recursive call stack in iterative backtracking algorithms. Subset generation is a classic backtracking problem. We want to generate all possible subsets of a given set of elements. To do this, we recursively decide whether to include or exclude each element from the current subset. Using STL vector makes this process efficient and straightforward because we can easily add or remove elements. With every recursive call, we explore one possible subset configuration, and if it's not valid or promising, we backtrack. The vector allows us to dynamically adjust our subset as we explore different paths. Here's the code for generating subsets using recursion and STL vector. Each recursive call will either include the current element or exclude it, and the results will be stored in the vector. Notice how easy it is to push and pop elements from the vector, which makes it a perfect fit for backtracking. This approach ensures that we explore all possible subsets efficiently. Another classic problem where backtracking shines is permutation generation. In this case, we need to generate all possible arrangements of a set of elements. We start by fixing one element in the current position and then recursively generate permutations for the remaining elements. STL vector helps us manage these arrangements in place, and backtracking ensures that once we explore one permutation, we revert any changes and explore other options. This is a great example of how STL can make recursive algorithms both simple and efficient. Here's a code snippet for generating permutations using STL vector. The key idea is to swap elements into the current position, recurse, and then swap back to undo the change. This process is repeated for all elements. STL's vector simplifies this task by providing dynamic array-like behavior, and the swap function is used to manage the element's position. Notice how this approach avoids the need for extra memory allocation, which makes the algorithm both time and space efficient. Now let's move to a more complex example, solving the n queens problem using backtracking. In this problem, we need to place n queens on an n cross n chessboard in such a way that no two queens threaten each other. We use a vector to track the positions of the queens on the board, and we use sets to track which columns and diagonals are already occupied. This allows us to quickly check if placing a queen at a particular position is valid. The power of STL lies in how it helps us manage the state of the solution efficiently and avoid redundant calculations. Here's a code for solving the n queens problem using backtracking and STL containers. We maintain three sets, one for columns, one for the first diagonal, and one for the second diagonal. These sets allow us to efficiently check if a queen can be placed at any given position. After placing a queen, we recurse to the next row. If we reach a point where no valid position is found, we backtrack and try another column. STL makes managing the state and checking constraints much easier. Now it's your turn to practice. Try implementing recursive solutions for these problems on your own. Start with generating all subsets of a string. Once you are comfortable with that, move on to generating permutations, making sure to handle duplicates properly. For an additional challenge, try solving Sudoku using backtracking or implement a word search solver. These problems will really test your understanding of recursion and backtracking combined with STL. To summarize, today we have seen how STL containers like vector, set, and map can be used to simplify backtracking algorithms. These containers help manage the state, track constraints, and make the code cleaner and more efficient. Backtracking is a powerful technique for solving many types of constraint-based problems, and STL helps you implement these solutions quickly and easily. Next up, we will be diving into some advanced practice problems. This will challenge your skills in STL, recursion, and backtracking, and are perfect for preparing for coding interviews and competitive programming contests. Get ready to solve complex, real world problems that combine multiple techniques in interesting ways. Welcome to day 34 of our STL course. Today we are diving into advanced practice problems designed to challenge and enhance your understanding of the standard template library. As you work through these real-world challenges, you will get the opportunity to apply your knowledge of STL containers, algorithms, and optimization techniques to solve complex problems. By the end of the day, you will feel more confident and ready to tackle any STL-based problem. Before we dive into the problems, let's quickly review the key learning objectives for today. By the end of this session, you will have learned how to solve complex problems using STL containers like vectors, maps, and DQs. You will also deepen your understanding of STL algorithms and how to use lambda functions and custom comparators to fine-tune your solutions. This day is all about practical application, so expect to walk away with the skills needed to tackle real-world problems efficiently. Now let's discuss an efficient problem-solving strategy for using STL. First, it's essential to understand the problem thoroughly. Identify the constraints and break the problem into smaller subproblems that can be tackled using STL containers and algorithms. Next, choose the right container, vectors for dynamic arrays, DQs for quick insertions or removals, or maps for key-value pairs, and of course use STL algorithms to streamline your code. Finally, always focus on optimizing your solution for both time and space complexity. By following this strategy, you will be able to approach any STL-based problem methodically and efficiently. Our first problem is sliding window maxima. Here we are given an array and a window size k, and our task is to find the maximum value within each sliding window of size k. This problem is often encountered in real-time monitoring systems, like tracking the highest stock price over a set period or monitoring CPU usage in a system. We can solve this problem efficiently by using a DQ to store the indices of array elements and ensure that the maximum element in the window is always accessible. The advantage of this approach is its n time complexity, which is far more efficient than brute forcing it with nested loops. Moving on to the frequency sort problems, where we are tasked with sorting a collection of elements based on their frequency of occurrence. The catch, in case of a tie in frequency, we need to sort the elements themselves. This problem is common in tasks like ranking or categorizing data, where we need to identify and prioritize the most common items. We can use an unordered map to count the frequency of each element and a priority queue or max heap to sort elements by their frequency. Custom comparators allow us to handle the tie breaking by sorting elements alphabetically or numerically. This gives us an efficient and customizable solution. Problem 3 challenges us to find the top k most frequent words from a list. This is a natural extension of the previous problem, but with the added complexity of only returning the top k elements. Think of it as identifying top trending keywords from a body of text. Again, we will use an unordered map to count word occurrences and a priority queue to efficiently retrieve the k most frequent words. We will also use a custom comparator to handle situations where multiple words share the same frequency, ensuring they are sorted alphabetically. This problem is very useful in text analysis, search engines, or social media sentiment analysis. Next, let's tackle the group anagrams problem. We are given a list of strings and our task is to group all the anagrams together. The key to solving this problem is recognizing that anagrams, when sorted, will have identical character sequence. By sorting each string and using the sorted string as a key in an unordered map, we can easily group all anagrams together. This approach is commonly applied in tasks like spell checking or deduplicating text data. It's an efficient solution that can handle large datasets with minimal computational overhead. Problem 5 asks us to sort string P based on the custom order provided in string S. This problem requires a custom comparator where the sorting order of T is determined by the sequence of characters in S. A priority queue can help us achieve this ordering, and we will need to create a mapping of each character's position in S. This type of sorting is often useful in scenarios like localized sorting, where elements must be ordered based on specific linguistic or cultural rules. In our bonus problem, we need to schedule tasks while respecting a cooldown period between executions of the same task. This problem is common in task scheduling systems like CPU scheduling or event-driven applications where tasks must be spaced out to avoid overload. We can solve this problem using a priority queue to select the next task to execute and an unordered map to keep track of the remaining cooldown time for each task. This approach ensures we handle tasks in the optimal order while respecting the cooldown requirements. Now let's talk about some useful debugging and optimization tips. First, prefer using unordered map over map when you don't need the elements to be ordered, as it offers faster access times. Avoid unnecessary copying or sorting, especially when working with large datasets, as this can lead to performance bottlenecks. When working with large data, take advantage of STL algorithms like copy if and remove if to simplify your code and reduce the need for manual loops. Lastly, always profile your code with large inputs to catch any performance issues early and fine-tune your solutions. Now it's your turn to put your skills to the test. Choose one of these exciting hands-on challenges. Implement an LRU cache using unordered map and list. Create a music playlist manager using STL containers, or build a leaderboard using set or map with custom rules. These challenges will help you apply all the concepts you have learned today and reinforce your ability to use STL effectively in real-world scenarios. As we wrap up day 34, remember that solving advanced problems with STL is all about applying the right tools and algorithms in the right way. STL provides powerful containers and algorithms that make it possible to solve complex problems efficiently and elegantly. Keep experimenting with new problems, focusing on both performance and readability, and continue challenging yourself to master STL. You are now ready to take on even more advanced problems, whether in coding competitions, interviews, or real world projects. Welcome to day 35 weekly assessment for the STL Mastery series. Today we are taking a step back to assess your progress and solidify your understanding of the essential STL tools we have covered in week 5. This assessment will test your grasp on pair, tuple, bitset, optional, variant, and more. You will tackle multiple choice questions, code tracing challenges, and coding exercises to ensure you are ready for the final weeks ahead. Today's goals are simple but essential. We will evaluate your theoretical understanding of STL tools, ensuring you are comfortable with key concepts. You will put your practical coding skills to the test through coding challenges and problem-solving exercises. You will identify areas that need extra attention before we move into the final stages of the course. This is your opportunity to assess your strengths and pinpoint areas for further improvements. So let's dive into the assessment. Here's how we will structure today's assessment. Part A. The first part consists of 10 multiple choice questions that will test your understanding of STL concepts. Each question focuses on specific topics like bitsets, optional types, map, operations, and more. Part B. Next we will have 5 code tracing problems. This will ask you to analyze a piece of STL code and predict its behavior. It's your chance to demonstrate how well you understand STL containers and algorithms in action. Part C. In 3 coding challenges, you will apply your skills to real-world problems, solving them using STL tools like pair, tuple, map, and others. Part D. Finally, there's an optional mini project for extra credit. If you want to earn bonus points, this project will allow you to showcase your creativity and problem-solving skills with STL in a more complex scenario. Here are a few sample questions from Part A to give you a sense of what to expect. What happens when you apply the XOR operator to 2 bit sets of the same size? How does optional differ from variant, and when would you use one over the other? If you wanted to store different types of data, How would you use tuple to make your data structures more efficient? These questions will test your ability to recall theoretical concepts and distinguish between related STL tools, so be sure to pay close attention to the details. Now let's move on to part B, which consists of code tracing problems. For example, you may be given a code snippet where you are asked to trace the output of a program that uses a vector of pairs and sorts it based on a custom comparator. This is an important skill. Being able to predict the behavior of STL algorithms and containers in real time will make you a more efficient programmer. The goal here is to evaluate how well you understand the flow of STL operations. In coding problem 1, you will write a function called filter event that processes a vector of integers. The function should return a vector of optional int where even numbers are wrapped in optional int and odd numbers are represented as null OPT. This problem tests your understanding of optional and conditional handling. It's a great opportunity to solidify how optional values work and how you can conditionally wrap or skip certain values based on their content. Next, we have coding problem 2, which is all about grouping data. You will need to organize a set of student records containing roll number, name, and grade into a map based on their grades. The map will use char keys for the grade and store a vector of tuples for each student in that grade. This challenge tests your ability to manipulate map, tuple, and vector and how to efficiently. Welcome to day 36 of the STL Mastery course. In this lesson, we will explore how the standard template library STL can be used in real-world application design. STL isn't just for academic exercises or coding competitions. It's a critical tool in scalable and efficient application development across industries. Today we will look at how to structure real systems using STL containers, algorithms, and techniques to solve real-world problems. Let's jump in. By the end of today's session, you will be able to integrate STL into your application designs effectively. Especially, you will learn how to leverage STL to optimize performance in real-world systems, combine multiple STL components in a structured, efficient way to meet your application's needs. Make design decisions by choosing the right containers and algorithms for the right use cases. Explore how STL is used in real-world open source projects, allowing you to see how these concepts are applied in industry. So let's get started with some foundational understanding of how STL fits into real software engineering. STL is not just an academic tool, it's an integral part of real-world software engineering. STL is widely used in industries like gaming, finance, embedded systems, and web development. For example, game engines rely on STL containers for efficient data management, and fintech applications use it for high-frequency trading algorithms. Even web servers use STL to manage large amounts of data quickly and effectively. STL helps solve real-world problems by providing optimized data structures and algorithms that can handle complex, large-scale applications. In modern software design, modularity is key to scalability and maintainability. STL supports modular design by offering flexible containers and algorithms that allow us to decouple different parts of the application. For example, in a task manager application, the data layer could use a map to store tasks by name, and a multi-map could be used to store them by deadline for easy sorting. For managing task priorities, a priority queue could be used. A stack or vector might handle undo actions, storing previous task states for recovery. This modular approach not only ensures that each part of the system is optimized for its task, but also makes it easier to scale as the system grows. Let's look at a real-world example, a task manager application. Imagine you need to manage a list of tasks with the ability to add new tasks, sort them by deadline or priority, search for tasks by keywords, implement undo, redo actions. For this, you can use STL containers like map, string, task to store tasks efficiently by their name. Priority queue to always retrieve the highest priority task. Stack action to implement an undo or redo system. Vector to keep an ordered list of tasks based on a certain attribute. This combination of containers ensures the system is both efficient and flexible. Here's a high-level architecture of our task manager. We can structure the application as follows. Task storage. In map, string comma task allows us to store tasks by name, providing log and lookup times. If we want to track multiple tasks with the same deadline, a multi-map date comma task could help us manage them in a sorted order. Undo functionality. By using a stack action, we can push every change to a stack, allowing us to pop the last action when the user hits undo. This ensures we can easily revert the state. Priority-based task sorting. A priority queue can help us always retrieve tasks in the order of their priority level, ensuring that critical tasks are addressed first. This architecture keeps our code clean, decoupled, and ready for future enhancements. A key to designing high-performance applications is choosing the right container for the right task. STL offers many options, and understanding the trade-offs between them can significantly impact our application's efficiency. For example, unordered map is faster for lookup operations than map because it uses hashing instead of sorting, but it does not maintain the order of elements. Vector is cache-friendly and efficient for random access and iteration, whereas list is optimized for frequent insertions and deletions. DQ is useful when you need fast insertions and deletions at both ends, unlike stack, which restricts access to the top element only. Choosing the right container depends on our application's requirements, such as the frequency of operations, memory usage, and performance needs. Performance tuning is essential when designing real-world systems. STL provides several tools to optimize performance. Using rewards with vector helps minimize unnecessary reallocations when elements are added, improving performance for large datasets. Move semantics can avoid unnecessary copies of objects, making your application more memory efficient and faster. For operations that need fast access, vector is often preferred, while for random insertions, list may be more suitable. Lastly, STL algorithms are designed to be highly optimized, often outperforming manual loops or custom implementations. By carefully considering performance at the container and algorithm level, we can make our application both fast and scalable. STL is widely used in several major open source projects. For example, Git, the version control system, uses STL containers in its index and TIFF modules to manage and compare large datasets efficiently. OpenCV, the popular computer vision library, relies on STL containers like vector and map to store and process image data efficiently. Game engines uses STL containers such as unordered map and priority queue for tasks like pathfinding and game state management. These real-world examples demonstrate STL's versatility and power in solving practical engineering challenges. Now it's time for you to apply what you have learned. Your hands-on project for today is to build your own task manager application using STL. You will need to implement features like adding tasks and sorting them by priority using map and priority queue. Implementing undo redo functionality with stack to track changes. Optionally add a tag search feature using unordered multimap. This project will give you a practical understanding of how to integrate STL into a complete application design. To summarize what we have learned today, STL is a powerful toolkit for real-world applications. By choosing the right containers and algorithms, you can build highly efficient and scalable systems. Containers like map, vector, priority queue, and stack can be combined to solve complex real-world problems. Performance can be optimized through careful container choice, move semantics, and effective use of STL algorithms. STL helps us write modular, maintainable, and high-performance code. Your assignment for today is twofold. Build a personal finance tracker. Use STL containers like map, multimap, and stack to manage financial transactions and generate reports. This will help you understand how to store, organize, and manipulate data effectively. Research STL in open source projects. Choose an open source C++ project like LLVM or OpenCV and explore how STL is used. Summarize its role in various modules and how it contributes to performance and design. This exercise will deepen your understanding of STL's applications in real-world systems. That concludes day 36. Today we explored how STL can be applied to real-world software design, from task management systems to performance tuning. The tools you have learned today are the building blocks for designing scalable and efficient systems. Don't forget to complete your assignments, and I will see you in the next lesson. Keep coding and stay curious. Welcome to day 37 of the 42-day STL Mastery series. In this session, we are diving into one of the most exciting and practical uses of STL, competitive programming. Competitive programming requires speed, accuracy, and an efficient approach to problem solving. And today we will focus on how the standard template library can give us a significant edge in coding competitions. From optimizing our code's performance to reducing the amount of boilerplate code, STL is indispensable in the world of programming contexts. Let's get started by exploring why STL is crucial in SCP. Competitive programming is all about solving problems under strict time constraints, often with large input sizes. This means every second counts and we need to work smarter and not harder. STL is a powerful tool in this context because it provides us with pre-built data structures and algorithms that are both efficient and optimized. By using STL, we can avoid having to write complex data structures from scratch. For example, containers like vector, map, and set are implemented with optimal time complexities. This not only saves time but also ensures our solutions are robust and run within time limits. Plus, STL's optimized algorithms such as sort, binary search, and accumulate are tested and efficient, allowing us to solve problems in a fraction of the time compared to writing our own algorithms from scratch. In competitive programming, we will work with a set of key containers that should be part of our toolkit. This includes vectors, sets, maps, unordered maps, priority queues. Let's break them down. Vectors are used for dynamic arrays that can grow or shrink in size, perfect when we don't know how many elements we need at the start. Sets and unordered sets are unordered collections with no duplicates, while unordered sets provide faster access via hashing, especially useful for problems requiring fast memberships. Maps store key value pairs, and unordered maps are optimized for fast access, making them perfect for problems involving associative data. Priority queues. These are special queues where the largest or smallest element is always at the front. They are essential for problems requiring greedy algorithms or scheduling tasks. DQ, a double-ended queue that allows you to add or remove elements from both ends efficiently. These containers allow us to write faster, more efficient code while handling a variety of problem-solving scenarios. Now let's talk about STL algorithms, which are just as important as the containers. STL offers a wide array of algorithms that help us solve problems quickly and efficiently. Sorting. The sort function is a common tool in many competitive programming problems. It's implemented using an efficient algorithm, typically intro sort, which has a time complexity of n log n. Binary search. Algorithms like binary search, lower bound, and upper bound help us search through sorted data in logarithmic time. This is crucial when dealing with large data sets. Accumulate and iota. Accumulate sums up elements in a range, and iota initializes a range with sequential values. These algorithms are incredibly useful when you need to perform operations on ranges efficiently. Next or previous permutation. These algorithms help us generate all possible permutations of a set, which is essential in combinatorial problems. These built-in algorithms not only simplify our code but also ensure that our solution is as efficient as possible. STL isn't just about knowing the containers and algorithms, it's about using them smartly. There are several STL tricks and idioms that will help us solve problems more efficiently and with cleaner code. Emplace back versus pushback. Emplace back constructs an element in place which can be faster than pushback, which requires copying or moving the element. Erase remove idiom. This is a powerful technique used to remove elements from a container. Instead of looping through and manually deleting elements, the erase remove idiom lets us remove elements in a single line of code. Custom comparators. STL allows us to use custom comparators when sorting containers. This is incredibly useful when we need to sort data in a specific order. Count if any of all of. These algorithms allow us to check conditions on ranges of data in a very readable way. They can help us avoid writing custom loops and make our code more declarative. These tricks will save our time and make our code more efficient and readable. Fast input and output handling can significantly impact the performance of our solution, especially in problems that involve large amounts of data. By default, C++ streams like C in and C out are synchronized with C's stdio, which can slow down input-output operations. To speed up things, we can disable synchronization with iOS sync underscore with stdio false and untie cin from cout with cin.tie null. This ensures that IO operations are faster and we can handle large datasets more effectively. In situations where performance is even more critical, using scanf and printf may offer an additional speed boost. Just remember that efficient I/O is often the difference between passing and failing time limits in competitive programming contests. Let's look at a problem we might encounter on platforms like Codeforces, finding the number of pairs ij such that I is less than j and ai plus aj modulo k equals to 0. This is a classic problem that can be solved efficiently with STL. The brute force approach would involve checking all pairs, which is slow for large inputs. Instead, we can use an unordered map to store the remainders of the elements. For each element, we calculate the remainder and check how many previous elements have complementary remainders to form a divisible sum. This reduces the time complexity from n squared to n, which is a huge improvement. Here's another problem, finding the maximum element in each sliding window of size k. The brute force approach would be to iterate over every window and find the maximum in each, which would take n times k time. However, we can solve this problem in n time by using a dequeue. We maintain a dequeue of indices of the elements in the current window. The dequeue is kept in decreasing order, so the front of the dequeue always holds the maximum element for the current window. When the window slides, we efficiently update the dequeue by removing elements that are no longer in the window and adding the new element. Now let's discuss some STL best practices for competitive programming. First, always be aware of the time complexity of operations for each container. For example, inserting into a vector in constant on average, but inserting into a set is log n. Redefine templates for common patterns like binary search or sliding window problems to save time during contests. Also avoid unnecessary copies of large containers as this can degrade performance. Instead, pass containers by reference whenever possible. Finally, custom comparators are a powerful tool for sorting, and handling edge cases properly is crucial in any solution. Now that we have learned the theory, it's time to practice. Here are a few competitive programming challenges to apply your STL knowledge. LeetCode's top k frequent elements, Codeforces, Pashmark and flowers, at Coder's ABC's sliding puzzle. These problems require efficient use of STL containers like unordered map, set, and vector. Try solving them using only STL to reinforce what you have learned today. As you practice, focus on how STL reduces the complexity of our solutions and speeds up our problem-solving process. That brings us to the end of today's lesson. We have learned how STL containers and algorithms can be a game changer in competitive programming. We discussed STL's role in simplifying problem solving, speeding up coding, and optimizing performance. In the next session, we will explore how to apply these skills in real-world competitive programming platforms like LeetCode and Codeforces. Keep practicing and you will soon find yourself solving problems faster and more efficiently than ever before. Great job today, and I will see you in the next session. Welcome to day 38 of our STL course. Today we are going to explore how to apply the standard template library STL in competitive programming environments like Codeforces and LeetCode. If you have ever participated in coding contests or tackled challenging algorithmic problems, you know that efficiency and fast thinking are key. STL provides a rich set of tools, containers, algorithms, and utilities that are indispensable for solving complex problems quickly. In this session, we will dive into practical examples from these platforms and explore how we can leverage STL to enhance our problem-solving approach. Competitive programming platforms such as Codeforces and LeetCode are the perfect arenas to hone your coding skills. First and foremost, they offer immediate feedback on your solutions, helping you quickly identify areas for improvement. But the true value lies in the time constraints. Coding under pressure mirrors real-world scenarios like job interviews or hackathons, where every second counts. These platforms also encourage pattern recognition by solving numerous problems. You will start seeing recurring themes and techniques. STL, when practiced on these sites, becomes second nature, and you will be able to apply it instinctively. The more problems you tackle, the better you will understand how to utilize STL's various tools efficiently. Let's discuss the key components of STL that are most useful in competitive programming. STL containers like vector, set, map, and unordered map are the go-to structures for storing and manipulating data. For example, unordered map provides constant time lookups, making it perfect for problems that require fast element access. STL algorithms like sort, binary search, and lower bound streamline common operations, saving you time and effort in implementing them manually. Lastly, utility components like pair, priority queue, tuple, and bitset allow for more specialized operations such as handling pairs of values, managing priority queues, or efficiently performing bitwise operations. Understanding how and when to use these tools is critical for solving problems in competitive programming. Let's take a look at a basic yet insightful problem from LeetCode. Find the element that appears more than n by 2 times in an array. This is a problem where an unordered map shines. As we iterate through the array, we count the frequency of each element. If any element exceeds n by 2 appearances, it's our answer. The unordered map allows for fast lookups and insertions, providing an efficient solution for this type of frequency-based problem. The problem is simple, but it demonstrates the utility of a basic STL container in solving real-world problems. Now let's examine a slightly more advanced problem from Codeforces. Find the most frequent two-letter substring in a given string. To solve this, we can use a map to store each two-letter substring along with its frequency. Once we have all the substrings, we can use max element to find the one with the highest frequency. Notice how the map provides automatic sorting by key, which is incredibly useful for problems where order matters. This problem teaches us how to combine STL containers with algorithms to efficiently solve string-related tasks. Next, we will tackle a well-known problem from LeetCode, the sliding window maximum. The task is to find the maximum value in every sliding window of size k. This is a perfect scenario for using a dequeue. A dequeue allows us to maintain the current window's maximum value while efficiently removing elements that fall out of the window and adding new elements. The sliding window technique is a common pattern in coding contests, and with the help of STL's dequeue, we can solve this problem in linear time, making it much more efficient than a naive approach. Here's another interesting challenge. Can a subset sum to a given target? This is a dynamic programming problem, and we can use a bitset to solve it efficiently. A bitset allows us to track which subset sums are achievable as we process the array. Each bit in the bitset represents whether a specific sum can be made using some subset of elements. This bitwise manipulation technique can dramatically reduce both time and space complexity compared to traditional dynamic programming solutions. The problem highlights how STL's bitset can be used for efficient set operations, especially when dealing with binary states. Now that we have explored some problems, let's discuss strategies for using STL effectively in coding contests. One important tip is to understand the time complexities of the containers we are using. Unordered map has constant time complexity for lookups, whereas map has logarithmic time. Additionally, pre-coding input-output templates can save you precious minutes during a contest, as input parsing and output formatting can often be a bottleneck. Another great tip is to practice using lambdas and custom comparators for sorting. This can significantly reduce the verbosity of our code. Lastly, avoid nested maps unless absolutely necessary, as they can lead to inefficiencies in both time and space. Also, when inserting into containers, prefer using mplace instead of insert, as it constructs the element in place, avoiding unnecessary copies. To reinforce what we have learned today, here are a few practice problems to tackle on different competitive programming platforms. On LeetCode, try problems like toSum using unordered map and longest substring without repeating characters, where using set can make a big difference. On both forces, challenge yourself with problems like watermelon and sticks. As you work through this, pay close attention to how you are using STL containers and algorithms. The more you practice, the more natural it will feel to use STL in different contexts. Let's summarize the key takeaways from today's lesson. STL is an invaluable tool for competitive programming, offering a suite of containers and algorithms that help you solve problems faster and with less code. We saw how containers like unordered map, and DQ are perfect for tasks such as frequency counting, sorting, and sliding window problems. The key is to identify which STL tool is best suited for each problem, and over time, you will develop an instinct for using the right tool at the right time. With consistent practice, STL will become a nature of your problem-solving toolkit in competitive programming. For your homework, I encourage you to solve at least 3 of the problems listed earlier. As you solve each problem, try to pinpoint the STL concepts you are using, whether it's containers, algorithms, or utility components. After solving the problem, reflect on your approach and share your solutions, along with an explanation of your logic in the course forum. This will not only help reinforce your learning, but also give you a chance to engage with your peers and see different approaches at the same problem. Welcome to day 39 of our standard template library course. Today marks a significant milestone as we move from the theory to hands-on application. It's time to pull together everything we have learned about STL containers, algorithms, and functional tools in a real-world context. For today's project, you will be building a full-fledged application using C++. You will be choosing one of the following projects to work on: a task manager, a calendar scheduler, or a cache system. This is where you get to be creative, solve real-world problems, and showcase your skills. Let's dive into the 3 project options. First, we have the task manager. This is a great choice if you want to create an application that manages tasks and their priorities. You will be adding, sorting, and updating tasks in a well-organized system. Next, we have the calendar scheduler. In this project, you will create an application to help users organize events, ensuring that there are no scheduling conflicts and allowing users to view their calendar in different formats, be it daily, weekly, or monthly. Lastly, the cache system project will challenge you to create an optimized storage system. The goal here is to implement a least recently used LRU or most recently used MRU cache system, perfect for fast data retrieval in applications with limited memory. The choice is yours. Each project will allow you to apply your STL knowledge in unique and interesting ways. Choose the one that excites you the most and let's get started. Before you start coding, let's remind ourselves of the key STL tools that will help us in building our project. The containers are at the core of your project, allowing you to store and manipulate your data. For example, you might use vector for ordered collections, DQ for efficient insertions and deletions at both ends, or map for key value pairs. You will also use algorithms to manipulate the data in your container. For example, you can use sort to organize tasks, find to locate an event, or remove to delete items efficiently. Another powerful feature of STL is the ability to use functional tools such as lambda functions and custom predicates. These let you write cleaner and more flexible code. Don't forget about utility types like var for 2 elements and tuple for more than 2. You will see how each of these tools plays a vital role as you implement your project. Let's focus on the task manager now. In this project, you will be creating an application to manage tasks based on their priority, deadline, and status. The basic features include the ability to add tasks with specific attributes like name, deadline, and priority. You will also be able to update or delete tasks as necessary. Sorting is a key feature. Your task manager should allow users to sort tasks either by priority or by deadline. You should also implement functionality to filter tasks based on their status, like completed or pending, and allow users to search for tasks or by keywords. This will involve searching algorithms and sorting algorithms and will help you understand how to manage large datasets efficiently. Next up is the calendar scheduler project. This application will help users organize events in an efficient way. Key features include the ability to add events with details such as the event's title, date, time, and location. You can then implement the ability to search events by specific date ranges. One of the most important features of this project is to detect event conflicts. If two events are scheduled for the same time, the system should notify the user. You will also need to sort events by their date so users can see them in chronological order. Finally, the ability to view events in different formats, daily, weekly, or monthly, will add a lot of versatility to your calendar. Finally, we have the LRU cache project. This is particularly useful for optimizing performance in systems that require fast access to frequently used data. The core feature is that you will store key value pairs, allowing you to retrieve data in constant time, which is the gold standard for cache system. When the cache reaches its size limit, it should evict the least recently used item to make room for new data. The LRU technique ensures that frequently accessed data remains in the cache while rarely used data is removed. You can also configure the cache size and optionally visualize cache hits and misses. This project will help you understand how DQs and unordered maps can be used together for high performance data access. Here's a suggestion for your STL structures to use in each project. For the task manager, you can use a vector of tuples to hold task information. Each tuple would store details like the task name, deadline, and priority. This structure allows you to easily sort tasks and retrieve them based on specific attributes. For the calendar scheduler, a map works perfectly, where the keys are dates and the values are vectors of events scheduled for those dates. This ensures quick access to events on any given day. For the cache system, I recommend using a DQ to manage the order of elements combined with an unordered map to store key value pairs. This combination ensures fast access to cache data while maintaining the correct order for eviction. Before jumping into the code, take some time to carefully design your project. Start by defining the key classes such as task, event, and cache item, and identify the key attributes and methods for each class. This design phase is critical because it will help us structure our code and avoid unnecessary complications later. Think about how your STL containers will interact with each other and which algorithms you will use. For example, how will you handle sorting tasks? How will you search for events? A solid design ensures that your code remains clean, modular, and easy to maintain. Here are the criteria we will use to evaluate your project. First and foremost, we'll be looking for correct STL container usage. Make sure you select the appropriate containers for each task, whether it's a map, a vector, or a DQ. Your use of STL algorithms should be efficient and well implemented. We also care about the modularity of your design. The code should be organized into classes and methods that are easy to read and maintain. We will be looking for how efficiently you solve the problem, especially if you can handle large amounts of data quickly. Bonus points if you add a user interface or even a command line interface CLI to interact with your application. Now that you are ready, it's time to build your project. Start by picking the project that excites you most and sketch out your design. Begin implementing your solution using C++ 17 or 20, and remember to keep your code modular and well cemented. Once you are happy with your work, consider pushing it to GitHub to share your progress. This project is not only a great way to demonstrate your understanding of STL, but also an excellent addition to your portfolio. Good luck and enjoy the process of creating something amazing. You have got this. Welcome to day 40 of our STL course. Congratulations on making it this far. Today we will be diving into project reviews and optimization techniques. These concepts are incredibly important as they help you refine and enhance your STL based projects. You will learn how to assess your code, identify areas for improvement, and apply optimization techniques to improve both performance and clarity. So let's get started and make sure your projects are not only functional but also efficient and elegant. Before we dive into the details, let's take a look at what we will be covering today. First, we will review our STL based projects. This review will help us identify design flaws, performance bottlenecks, and areas where optimization is needed. Next, we will introduce a series of optimization techniques ranging from algorithmic improvements to memory management strategies. These techniques are critical for taking your code from functional to efficient. Finally, we will discuss the importance of code clarity and efficiency. Remember, optimizing your code isn't just about making it run faster, it's about making it easier to understand and maintain. To effectively review your projects, it's essential to have some solid evaluation criteria. These criteria will guide you through the process of assessing the quality of your work. Let's break down them. First, we need to evaluate if you have selected the right STL container and algorithm for the problem at hand. Choosing the correct data structures can make a significant difference in performance. Next, we will look at modularity and reusability. Is your code well structured and easy to reuse for other tasks? Naming conventions and readability are also key aspects. Your code should be clear and understandable at first glance. We also need to evaluate how your project handles edge cases. Does it account for all possible scenarios? Lastly, performance benchmarks are crucial. Are you using the most efficient algorithms and data structures? These benchmarks will help you identify bottlenecks in your code. As we review projects, it's important to be aware of common mistakes that can easily slip in. First, a big mistake is using manual loops when STL algorithms could be used instead. STL algorithms are optimized and can make your code cleaner and faster. Another issue is selecting the wrong container for the task. For instance, using a vector where a DQ is more appropriate can slow down performance. Additionally, using insert where emplace would be more efficient can lead to unnecessary copies. This can have a major performance impact, especially when working with large data. Lastly, it's important to be aware of complexity. Every decision you make, such as choosing a container or algorithm, has a time and space complexity. Ignoring these impacts can make your code much slower than necessary. Our first optimization tip focuses on algorithmic thinking. The STL is packed with highly efficient, pre-written algorithms that can save you a lot of time and effort. Instead of writing manual loops, consider using the appropriate STL algorithms like binary search, countif, or transform. These algorithms are not only more concise but are also optimized for performance. By using these built-in functions, you avoid reinventing the wheel and get the benefit of well-tested, efficient code. Algorithmic thinking allows you to approach problems more abstractly, making your code both cleaner and faster. Optimization tip number 2: choosing the right container for the job. This is crucial for improving performance. Let's take a closer look at this table, which outlines the preferred containers for various tasks. For example, if your task requires frequent insertions and removals at both ends, the DQ is a better choice than vector because DQ offers constant time insertions and deletions at both ends. For tasks that require fast lookups, an unordered map is a much better choice than map because it provides average constant time complexity for lookups, and for ordered fast inserts, a set or map is ideal. These containers are optimized for the operations they support, and selecting the right one can drastically improve your project's performance. Our third optimization tip is to use emplace rather than insert when adding elements to a container. The key difference is that emplace constructs the object directly in place, which avoids creating a temporary object. This can be a significant performance boost, especially when dealing with complex objects like pairs or tuples. Consider the example of inserting a large object into a map or vector. If you use insert, it will first create a temporary object and then copy it into the container, which is an unnecessary overhead. On the other hand, emplace constructs the object in place, eliminating the need for a copy. This small change can lead to much more efficient code. Optimization tip number 4 is all about memory management. When working with vector, you can optimize performance by reversing space ahead of time using reverse end. This helps avoid multiple reallocations as elements are added. If you know in advance how many elements you will be inserting, reversing space can save a lot of time. Similarly, shrink to fit can help free up memory that is no longer needed. For example, after removing a large portion of elements from a vector. Calling shrink to fit will reduce the capacity of the vector to match its size, freeing up unused memory. Proper memory management is essential for ensuring that your program runs efficiently, particularly when working with large datasets. Optimization tip number 5 is to avoid unnecessary copies. Passing large objects by value or copying them unnecessarily can severely degrade performance. Instead, always prefer passing objects by reference. And if you are not going to modify the object, pass it as a const reference. This ensures that you don't copy the object, which can be particularly expensive when dealing with large data structures. Additionally, when accessing elements from containers, make sure you are using references to avoid copying. This simple practice will make your code more efficient and less prone to performance issues. Optimization tip number 6 focuses on custom comparators and hashers. In cases where you are using custom types as keys in a set or unordered map, you need to define how these objects are compared or hashed. This is critical for performance as insufficient comparators or hashers can slow down the entire operation of the container. For example, if you are storing objects in a map, the default comparator might not be the most efficient for your data. You can create your own comparator optimized for your data type to improve lookup times and make your code run faster. Here's an example of code optimization. In the before code, we are manually iterating through the vector, checking if each element is even. This is fine for small data sets, but as the dataset grows, this approach becomes inefficient. In the optimized version, we use COUNTIF, a powerful STL algorithm to count the even numbers in a more efficient way. Not only does this reduce the complexity of our code, but it also takes advantage of the optimized internal implementation of COUNTIF, making the operation faster and cleaner. Now let's look at some real-world STL optimization case studies. In a leaderboard system where you need to maintain an ordered list of top scores, using a multiset can be very efficient. The multiset automatically keeps elements in sorted order, so you don't need to worry about sorting the list manually after every update. Similarly, in a task scheduling system, using a priority queue ensures that tasks are processed in the correct order based on their priority. Both of these cases highlight the power of STL containers and algorithms in real-world applications, where performance is key. It's now time for peer review and group feedback. Share your projects with your peers and discuss the design decisions you made. What STL containers and algorithms did you use and why? Are there any areas where you can optimize further? This is an excellent opportunity to receive feedback from others and refine your approach. Sometimes others can spot potential improvements that we might have missed. Take this time to learn from each other's experience and perspectives. To wrap up today's session, let's review the key takeaways. First, remember that your design decisions have a direct impact on performance. Selecting the right containers and algorithms is crucial for making your code efficient. Second, STL tools are incredibly powerful, but they must be used wisely. Familiarize yourself with the right tools for the job and leverage their full potential. And finally, always aim for clarity and efficiency in your code. Clean, readable code is just as important as performance, and a balance between the two is key to writing great software. Looking ahead to day 41, we will focus on mock interviews. You will have the chance to practice explaining your STL projects and optimizing in a real-time interview setting. This will test not only your technical skills but also your ability to communicate complex concepts clearly. Make sure to revise all the optimization techniques we have discussed today, as they will be useful in the mock interview. Prepare yourself to explain your design choices and optimization strategies in details. Welcome to day 41 of our 42-day STL Mastery course. Today marks an exciting milestone as we step into the world of mock interviews with a specific focus on the Standard Template Library or STL. In this session, we are going to simulate real-world technical interview rounds, solving problems using STL and applying it to solve algorithmic challenges. This is your opportunity to hone your interview skills and get ready to face the technical interviews that lie ahead, whether it's for a software engineer position at a tech giant or a startup. Let's get started and immerse ourselves in this interview simulation. Before we dive into the mock interview rounds, let's take a moment to discuss the objectives for today. The first goal is to simulate a real technical interview experience. You will be solving coding problems under pressure, just like you would in an actual interview setting. The focus of the problems will be on your ability to efficiently use STL, which is a critical skill in many coding challenges, especially for positions that require C++ proficiency. During the mock interview, you will be solving problems using STL algorithms, containers, and other related techniques. You will also practice under time constraints, mirroring the time-limited nature of real interviews. In addition to the coding rounds, we will provide peer and mentor feedback, allowing you to gain valuable insights into your approach, identify areas for improvement, and refine your skills for future interviews. By the end of this session, you should feel much more prepared for interviews that involve problem solving using STL. Here's an overview of what today's session looks like. We will kick things off with a brief welcome and briefing that lasts for the first 15 minutes. This will set the stage and I will walk you through the structure of the mock interview process. Then we will get into round 1 where you will face two timed coding problems. This round is focused entirely on solving problems using STL containers and algorithms. After that, in round 2, you will be presented with more complex problems that require not just coding but also design thinking. This means you will need to come up with a high-level solution, consider various design choices, and justify your approach. Once the coding rounds are complete, we will move on to peer review and panel feedback, where you will receive detailed input on your solutions and performance. Finally, we will conclude the day with a wrap-up session from the mentor who will share interview tips and strategies to help you succeed in coding interviews. Let's dive into each segment with enthusiasm. In round 1, you will face two timed coding problems. This round is designed to test your proficiency in applying STL to solve algorithmic challenges. Each problem will require you to choose the most appropriate STL containers and algorithms to optimize your solution. For example, one of the problems could ask you to find the k most frequent elements in a dataset. You will need to decide whether to use an unordered map to store element frequencies and a priority queue to find the top k frequent items. Another problem could involve the next greater element for this. A stack and a vector will come in handy. Lastly, a problem like sorting characters by frequency will require the use of a map, sort, and lambda functions. These are just a few examples, but rest assured, the problems will challenge your ability to apply STL effectively to solve real-world problems. During round 1, we will evaluate your performance based on several key criteria. First and foremost, we will look at how well you have used STL containers. Are you selecting the right data structures for the problem at hand? Are you using them efficiently? Secondly, we will evaluate the efficiency of your algorithms. Can you come up with a solution that is both correct and optimal, with a time complexity that does not exceed the problem's constraints? Next, we will focus on the clarity and readability of our code. In a real interview, interviewers need to understand your thought process, so writing clear, well-organized code is critical. Lastly, we will pay special attention to your use of idiomatic STL features, for example, using iterators to traverse containers and lambdas to make your code more concise and efficient. The goal is to demonstrate your understanding of STL and its capabilities while solving problems effectively. Moving on to round 2, this round will test both your coding and design thinking. Here, you won't just solve basic problems, you will also have to think about how to design a system or choose an optimal data structure for a given problem. For example, one problem might ask you to design a task scheduler using STL containers. In this case, you will likely use a priority queue to schedule tasks based on priority and a map to store tasks with their corresponding metadata. Another example could be designing an LRU cache. For this, you might use a list and unordered map to efficiently manage cache entries. In this round, you will not only code but also explain why you choose a particular STL container or algorithm. This will help demonstrate your ability to reason through design decisions, a skill that's essential in real-world software engineering. Once the coding rounds are complete, it's time for peer review and feedback. During this session, we will receive detailed feedback from your peers and mentors. The purpose of this feedback is to help you identify areas where you can improve your approach and refine your skills. For example, did you choose the best STL container for each problem? Was your solution both correct and efficient? Did you explain your thought process clearly? These are some of the key points that will be covered in the feedback. This is a valuable opportunity to learn from others, gain new perspectives, and further develop your problem solving skills. As we wrap up today's session, our mentor will provide a wrap up session where they will go over common pitfalls that interviews often face when using STL in interviews. For example, many candidates struggle with choosing the right container for a given task or optimizing the performance of their solution. Our mentor will also share some best practices for coding interviews, including how to approach problems methodically, how to think out loud during an interview, and how to manage your time effectively. We will also discuss strategies for managing interview pressure and how to stay calm under time constraints. Finally, we will provide you with hands-out that will be incredibly helpful as you continue your preparation, such as an STL interview cheat sheet and a list of top 10 STL coding questions. As we conclude today's mock interview session, let's go over the key takeaways. You have the chance you have had the chance to simulate a real STL interview environment, solving problems and receiving feedback. This practice should have boosted your confidence and equipped you with valuable insights into your strengths and areas for improvement. You have learned how to solve problems using STL containers and algorithms under time pressure, and the feedback from peers and mentors will help you fine tune your skills. Most importantly, we are now better prepared for coding interviews, not just for STL but for any technical challenges that come our way. Keep practicing and remember, real interviews are just as much about problem solving as they are about communicating your thought process clearly and confidently. Welcome to day 42, the grand finale of our STL journey. First and foremost, congratulations to each one of you for reaching this milestone. You have put in the efforts and you are here today because of your dedication over the past 6 weeks. This final day is all about reflecting on your progress, testing your understanding with the final quiz, earning your certification, and taking a moment to celebrate everything you have learned. Today we wrap up not just with a quiz, but with a recognition of your hard work and growth. Let's dive in. As we come to the end of this course, let's take a moment to reflect on the incredible amount of knowledge you have gained in these 6 weeks. In week 1, we started by exploring the foundational aspects of STL, understanding the importance of containers and iterators, and diving deep into vectors. Week 2 introduced the powerful concepts of stack, queue, dequeue, and list, and how each of these containers works under the hood, their performance characteristics, and their practical applications. In week 3, we took a deeper dive into maps, sets, and custom comparators, giving you the flexibility to handle data in a more advanced way. Week 4 was where we really started to see the magic of STL, working with algorithms like sorting, searching, and modifying data in a way that saves you time and effort. Week 5 introduced functional utilities, predicates, and explored how STL integrates with recursion and backtracking, preparing you for complex challenges. Finally, in week 6, we wrapped it all together, applying your STL knowledge in real world applications and exploring how STL plays a major role in competitive programming. You have covered a lot, and today we celebrate that. Now it's time to take the final quiz, and I want you to approach this with confidence. You have prepared for this moment, and it's your opportunity to showcase everything you have learned. The quiz consists of 30 questions, a mix of multiple choice questions and code-based problems, each designed to test your understanding of STL concepts in depth. You have 45 minutes to complete it, so stay focused and manage your time wisely. To pass, you will need to score 70% or higher, and you will receive instant feedback after each question, so you can learn from any mistakes. Remember, the goal isn't just to pass, it's to demonstrate your true mastery of STL. No external help or ID use is allowed during the quiz, so rely on your knowledge and trust in the work you have put in over the course of the program. Good luck and give it your best shot. Alright, it's time. Take a deep breath and relax. You have got this. Before you dive into the questions, remember to read each one carefully. Sometimes the way a question is phrased can be the trickiest part. Focus on the core principles of STL, whether it's container behavior, algorithm efficiency, or practical usage. Take your time, think through your answers, and trust yourself. You have studied hard, and now it's your turn to shine. Stay calm, stay focused, and let's see how well you have mastered STL. Congratulations on completing the quiz. Whether you nailed it or found a few tricky questions, what matters most is that you have reached the finish line. Now it's time to review your performance. Check your score and take a moment to understand any areas where you might have struggled. Instant feedback will give you valuable insights into your strengths and the areas you can improve. If you didn't pass, don't feel discouraged. This is all part of the learning process and you can always retake the quiz after revisiting the material. If you passed, fantastic work. You have truly earned it. Take a moment to reflect on how far you have come. This is the result of weeks of hard work and dedication. Now let's talk about your achievement. You have completed the course and demonstrated your skills, and you have earned the title of Certified STL Practitioner. This certificate is not just a piece of paper, it's a recognition of the effort, persistence, and skill you have demonstrated. It signifies that you are well versed in the standard template library and that you have the knowledge to use STL efficiently in real world applications. Be proud of what you have accomplished and remember this is just the beginning. Share your certificate proudly on LinkedIn, GitHub, or your resume. You have proven yourself capable, and this is something you should definitely showcase. Now let's reflect for a moment. What has been your favorite STL concept or tool? Was it mastering iterators and learning how to navigate through data structures? Or perhaps you enjoyed the power of algorithms or the flexibility of maps and sets? Take a second to think about the concepts that resonated with you the most. And don't just keep this journey to yourself. Share your experience with others. Inspire those around you to start their STL journey. Share your achievements on social media and perhaps help others who are just beginning. You have gained valuable knowledge and now it's time to pass that torch forward. While this course has come to an end, your learning journey does not stop here. You are now equipped with a solid understanding of STL, but there's so much more to explore. If you are interested in system design and low-level design, STL is just one piece of the puzzle. There are many more advanced topics waiting for you. You might also want to dive deeper into advanced C++ concepts such as concurrency, smart pointers, or memory management. Competitive programming is another excellent next step. Websites like Codeforces and LeetCode offer countless opportunities to challenge your skills in a fun and competitive environment. Thus, your understanding of STL will give you a significant edge, and of course, data structures and algorithms preparation is critical for any technical interview. With STL in your toolkit, you are ready ahead of the curve. As we wrap up, I want to take a moment to say thank you for being a part of this incredible STL journey. It's been an absolute pleasure to guide you through these weeks of learning, and I am so proud of how much you have accomplished. Keep pushing yourself, keep coding, and just stay curious. There's always something new to learn, and I know you are going to continue to grow as a developer. Best of luck with all your future endeavors, and I truly hope to see you in the next course. Take care and happy coding.